Hyderabad. So I'm really happy to be here. So a little bit of my journey. So I'll speak up again if you can't hear, tell me. So from Hyderabad, I lived here for the first 18 years of my life. Then I went to IIT Madras. I see a lot of people from IIT Madras here. I'm one of them. I did my undergraduate at IIT Madras. And then I moved to the US. So my master's was at the University of Illinois. Then I moved to Switzerland. There I did my PhD in ET at Zurich. Then I was at Oregon State University. So somewhere here for a couple of years. And then for the last 8 years or so, I've been at the University of Miami. So big picture, this is what we do as a group. So we do a lot of research, but I'm passionate about a lot of other things as well. That includes education, that includes mentorship, largely of faculty members. It includes workforce development. It includes regional innovation. So these are all things that we've been really getting into in the last couple of years, and I'm happy to discuss with you, but not necessarily research related. In terms of research, broadly, my expertise has been supplementary cementitious materials. That's what I worked on for about maybe 17 years now. And more recently, we've been working on coastal infrastructure and resilience for the last 4 or 5 years. I'm not an expert on coastal infrastructure or coastal resilience, but we're starting to increasingly work on the topic. So in terms of supplementary cementitious materials, we work on a number of different areas which are related to decarbonization, to processing, to activation, to looking at process structure property relationships, things like that. With respect to coastal infrastructure, we work on 3D printing, on deployment of naval infrastructure, QA/QC, process control, artificial coral reefs, seawalls, etc. So apart from that, we like to have a nice time. Life is not all about work. So we go out once in a while with the group. We do some nice things. Also, if you ever come to Miami, and I'll give you a reason to come to Miami, if you ever come to Miami, we make these little nice concrete things, whether they're fish, dinosaurs, or decorations, and we'll give them to you. Just something nice, just sort of. Just something nice so that you can take it, give your children, or keep it on your desk, something like that. Okay, I think a lot of you have already heard quite a bit about CO2 in concrete, so I'll be pretty short with this presentation. So why is it important to understand, to control the CO2 in concrete? Well, cement contributes about 6 to 8% of global CO2 emissions. You'll notice the slide says concrete, not cement, but really cement contributes 90% of concrete CO2 emissions, so it doesn't matter whether you say cement or concrete. Concrete may or may not be a destructive material, but the reality is that it is impossible to replace concrete with any other material. If someone says they can do so, they don't really know what they're talking about, or they're extraordinarily futuristic. Bottom line, we must reduce cement CO2 emissions. There's a lot of graphs here. I'm not going to go into the details, but what those graphs tell you is, in a sense, cement's emissions are pretty high, concretes are extraordinarily low. But regardless, when you compare to a lot of other materials, cement and concrete, when you plot embodied energy or embodied carbon, etc., are about as low as they can get. The reason for the very high emissions, of course, is that we use 20 billion tons or whatever of concrete. Any material that you use 20 billion tons of will have an emissions problem. There are many roadmaps in the US, in India, and otherwise that aim to reduce emissions by 40% or to go carbon neutral by 2030, 2050, etc. And there are various challenges associated with achieving or hitting these roadmaps. So let's take a little bit of a deep dive into where the CO2 emissions of cement come from. For many of you, you know this inside out. Anyway, the process to make cement is very simple. You take limestone, you take clay, you take some other materials. You heat that up to about 1400 or 1500 Celsius. So one part of the emissions, about 60% of it, comes across because you're heating the limestone, right? Limestone decomposes to give calcium oxide plus CO2. That's causing about 60% of the emissions. The remaining 40% of the emissions is because of the temperature, is because of grinding processes, things like that. There's a more detailed breakdown if you would like to take a look at it. So One very simple way to reduce emissions is don't add all the limestone here, right? Instead, add 5 to 15% of the limestone at the end so that you don't actually get the decomposition of the limestone, you add it during the grinding process. That generates what is known as a limestone cement or a Portland limestone cement, and in principle, this reduces about 10% of the CO2 emissions. There are so many interesting ways to reduce CO2 emissions in limestone. Dr. Netalath, the other day in this room, talked about electrification. So there's a lot of interesting things that you can do with electrification or with co-calcining things. One more question, this is for the audience. Why do we even use limestone? Can we replace limestone with something else? For the students, why don't you think about that? Is it possible to replace limestone with something else? Or, as an example, why do we even have to do all of this heating, cooling, etc. process? Are there other ways to make cement? And the answer is there are a lot of different ways in which you can do it. But many of these, and people are working on them. If you come talk to me later, I'll tell you a lot of startups, what they're doing, etc. But many of them, it's hard. They haven't tested so much at the concrete scale. So that these are really interesting technologies that need further studies. Before we look at very interesting, very new technologies, I think we should actually consider what we can do with technologies that exist today. It's very interesting to work on niche technologies, very cool technologies, but it does not matter if no one is using them or if their overall usage is maybe 0.001% of all concrete. We should rather also focus on technologies which are currently being utilized. So straightforward, use PLC. Use SCMs, use chemical admixtures, optimize aggregate gradations. All of these are well understood, but many times they're actually not used, even though they can be. I'm not saying it's trivial to use them. There are some barriers. For example, maybe you don't have the aggregates. Maybe you don't have the SCMs, right? Maybe the chemical admixtures are extremely expensive. Regardless, for projects, these are very straightforward things to do. Admixtures are a very easy way to control your water to cement ratio or to use lesser cement if that's what you choose to do. So use the standard techniques first. If you just do this, right, in theory, it might be possible to reduce the CO2 emissions of any given concrete by about 30% already compared to what we are doing. So that's a great first start, right? Let's work on things which we can improve right now instead of going towards very fancy ultra high performance concrete. So in case this is not something that you're doing, you should consider doing it right now. The other nice thing is this is not cutting edge science. We understand very well what the effects on concrete durability are. So these are all standardized things. So it's not that you have any barrier to adoption, at least in terms of standards and specifications. A little talk about supplementary cementitious materials. SCMs, these are typically amorphous industry byproduct calcium aluminosilicate materials. The calcium may or may not be there. You can also have SCMs without calcium, but aluminosilicates are needed. So typically these are byproducts of coal or steel or iron industry, although there can be naturally occurring supplementary cementitious materials as well. Now, SCMs are critical to reduce CO2. However, that's not the only reason you use SCMs. People have been using SCMs for a really long time. Even if you do not care whatsoever about CO2, you need to use SCMs in concrete because without SCMs, in most cases, it is impossible, if not almost impossible, to make sustainable and durable concrete. So the logic or the reason that you use SCMs need not be just CO2 emissions. Use SCMs because they make your concrete better. These properties improvements are largely related to later age properties, that is durability, but you can also have improvement in strength, improvement in fresh properties, etc. The most commonly used SCMs are fly ash, slag, and silica fume. But unfortunately, there's increasing shortages that are being reported of SCMs. So one critical thing is how to identify novel SCMs and how to use these. If you look at a global scale, calcined clays, natural pozzolans, and reclaimed fly ashes are your answer. Looking forward to the future, manufactured SCMs, either through thermal approaches, leaching approaches, mechanochemical approaches, these are also very interesting. So we wrote a paper a couple of years ago called Future and Emerging Supplementary Cementitious Materials. If this is a topic you're interested in, I suggest that you read this paper. It identifies a number of novel feedstocks and materials that can be used for future and emerging SCMs. Here is an entire list. I'm not going to go into detail on any of them, but you can try to look at some of these materials if that's of interest to you. And in theory, some of these may be very applicable for you, and otherwise may not be. But also thermal, mechanochemical leaching, CO2 exposure processes. These can be used to transform something that is not reactive, that is something that's a filler material, into a reactive SEM. And a lot of these processes are taking a lot of interest from various startups. I want to spend a little bit of time talking about SEM reactivity. Over the course of this conference, we've seen people talk about things like strength activity index, etc. Generally speaking, strength is not a good measure of reactivity. It's not a terrible measure, but it's certainly not a good measure. So my suggestion, and I'm happy to chat with you more after this, if you want to understand reactivity, why don't you measure reactivity? So you can measure reactivity quite easily, and you don't need expensive equipment. A simple furnace can tell you what the reactivity is. And if you have nice equipment, then run isothermal calorimetry, right? So the R3 test, which is standardized as ASTM C1897, is a way in which you can measure reactivity. In that test, you mix the SEM with calcium hydroxide, with potassium hydroxide, with carbonates and sulfates, and then you measure the bound water and or the heat release over time. We ran some modifications to this test. The modifications are honestly not that important, at least for a short presentation like I have right now. But we've measured the heat release. We've also measured the calcium hydroxide consumption. We've also measured bound water. For the purposes of this presentation, just know that having a heat release more than 100 joule per gram of SEM is a reactive SEM, or in terms of bound water, about 3.6%. So very simple test. Please, if you're evaluating new materials, run an R3 test or some modification thereof. The R3 is standardized, so there's a lot of benefit in running a standard R3 test in addition to the other tests that you may want to run. One of the most important technologies that is existing to reduce CO2 emissions and to provide sustainable and durable concrete is LC3. Many others have talked about it. I don't go into details here. But what is interesting here is the synergy between limestone and calcined clays. Both materials are hugely available. Calcined clays are extremely reactive. There are further reactions between limestone and calcined clay which really improve the strength, later age durability of this system. One of the things that is very interesting here is that the workability or the water demand of limestone calcined clay can be a little bit of a problem. So novel admixtures are being investigated by many for limestone calcined clay cements. Okay, so now I'm going to talk about a couple of different technologies that we are working on. The first is thermal activation. Very simple. Take an inert material, something that's not reactive. If you heat it and then cool it, basically you can make the material melt and then you can amorphize it. This, of course, really depends on how you quench the material. The quenching rates have an important effect. But we have done this in a couple of cases, and we've found that we can melt basaltic materials, etc., to make supplementary cementitious materials. Many others have worked on clays. And you'll tell me, oh my God, Pranay, this is a lot of energy. It'll never scale. Well, it can actually scale, and there are companies, Terra CO2 is one of these companies, that is doing it at an industrial scale. They do it in a different system. It's known as an in-flight vitrification system, and they've used a number of different feedstocks. Basically, in that one, materials go up in a chamber, and the heating is very, very rapid. But then the cooling is also rapid, and they can get spherical particles like fly ash, so synthetic SEMs. It's not, there's very interesting science. Some studies have been done, but basically, a number of different materials can be activated and then cooled down to generate supplementary cementitious materials. Really, we have looked at low kalinitic clays and basalt fines. But more broadly, we are also interested in mine tailings, and we are also interested in all sorts of other quarry fines. So some of the interesting things in these technologies are what is the role of calcium? Because calcium essentially changes the nature of the glass that is formed. So it, in principle, increases reactivity, or at least reactive kinetics. So a reaction kinetics. So the role of calcium is interesting. Blending SEMs is interesting. Dr. Nethalat also talked about these core shell structures. So depending on how you do things with partial melting, you can create some core shell structures which can have very interesting reactivity. Quenching has not been studied, in-flight approaches, etc. Lots of additions and process modifications can be done to increase energy efficiency or reactivity or improve workability. All of this has to be studied. but we generated various materials which were adequately reactive based on the R3 test using this approach. Second different approach I want to talk about is mechanochemical activation. So mechanochemical activation is a little different from your normal grinding, because this is grinding that is done at very high energy. We are talking about 400 RPM, which is about 4 to 10 times the RPM in your standard grinding. You also use very tough media. We've really looked at basaltic fines, mine tailings, and clays, but many other materials are of interest. And two companies, Carbon Upcycling and Polysius, are doing this at scale, although I don't exactly know how they're doing it. Most have focused really on clays. In this talk, and we are also interested, in this talk I'll talk a little bit about basaltic fines. And mechanochemical activation can also be combined with CO2. That is, while you're grinding, you put CO2 into the system, or with other thermal approaches, things like that. The nice thing about mechanochemical activation is basically that the changes that you're getting are not just physical. You are actually amorphizing the material. So you're taking a crystalline material and you're making it amorphous because of the amount of energy that you're putting in. So I don't want to go into too much detail here. I don't have the time. But what we see is that in many cases, as you start grinding it, the specific surface area as measured from BT increases, and then it either reduces or then it levels off. So there's a lot of study that is done on this phenomenon. But basically, the idea is beyond a certain point, because of the energy, you're getting some sort of an aggregation, agglomeration phenomenon. Some would also argue and call it sintering. Because of high temperatures, your particles can kind of partially melt and stick together. Regardless, we see in almost every case, increase in the BET and then a reduction. And basically, here's a paper. You can read that paper if you're interested. I'm happy to send it to you. So we did a whole bunch of SEM on a number of different particles, not just this. And in every case, we see three things. One is that we generate a very wide range of particles. The particle sizes we see like nanofines to really large particles. Two is that we see spherical particles. So after the grinding, the particle shape becomes somewhat like a sphere. And three, we see very clear evidence of aggregation and agglomeration. That is, particles are sticking together. And I'm saying both aggregates and agglomerates because some of these are easily dispersible, others not so much. So it is no surprise that we are amorphizing the material. So we start with a material that has about 14 to 20% amorphous content, and we end up with a material that has about 50 to 95% amorphous content, broadly speaking. That's not the interesting thing. The interesting thing is that the amorphization basically follows the hardness of the phases, meaning if we start with a material that has 5 different phases of 5 different hardness, essentially the first phase that becomes completely amorphized is the softest phase. And something that's very hard, something like a quartz, for example, is not easily amorphized. If anything, it probably acts as an inclusion. So basically, we see this heterogeneous amorphization that seems to drive mechanochemical activation. And we looked at reactivity. And in every case, we see that as we increase time and some other parameters known as ball-to-powder ratio, the reactivity increases, and we get pretty significant reactivity, similar to most commercial slags or fly ashes. The most interesting thing in this sort of behavior is that we plotted the heat release or the reactivity versus specific surface area, and we find no relationship. Normally, you think that specific surface area increases reactivity. In this case, it has a negligible effect. Instead, it's the amorphous content that drives reactivity. That is, we find that the reactivity shows almost a linear relationship with the amorphous content. We have a lot more points than this, but the data is generally similar. So basically what's happening is we really show that in this process, as we amorphize, it directly generates reactivity. I showed you one material. What about other materials? We've tested 20 plus materials, and I don't want to say that you can do MC on everything. That's not the point. You really should do it on materials which are inert, because if you do it on materials which are already reactive, you get almost no benefits, and the energy input is fairly large in mechanochemical activation. I don't have it here, but if you're interested, I'll find the paper and get you the values. But at least at a lab scale, our energy values are fairly high. Okay, these are some technologies, but I want to talk about some more technologies. You can do leaching. You can do enforced carbonation. You can make bio-based cements, other new cements. There's calcium carbonate, vaterite-based cements, geopolymers, calcium aluminate cements, CSA cements, BCSA cements, B-lytic cements, CCUS. All of these technologies can help. Again, it's not just CO2, right? It's CO2, but also in making new concrete, in making concrete that is resilient, in making concrete that's durable, etc. I put a number of companies here. I don't necessarily endorse what they're doing or anything like that. I just wanted you to be aware of some of these companies. Okay, very good. You're making new concrete. So what? Well, remember that you really need to understand durability as well. It can't just be testing at small scale. And this is a picture that I like to show. Okay, how you test becomes very, very important. If you take an egg and you put it under a hen, normal low temperature goes slow, you get a chick. If you take that same thing and if you put it at high temperature at 80 Celsius in a pan, you get an omelette. Okay. The point is not that they are different, but the point is that they are not interchangeable. This cannot go to this, nor can that come to this. Okay. So when you run chemistry tests or durability tests, the thermodynamics is important, the kinetics is important. When you run tests ignoring those, you get results that don't make much sense. So accelerated testing takes time, is not always accurate. Standard concrete durability tests are not always applicable for new materials. We need to do structural testing. Many new materials are not covered by specifications, so we need to make sure that they are. Chemical admixture compatibility, FRP, UHPC, 3D printing, all of these are things that you want to consider with some of your new materials. I'm almost done. So broadly, I highlighted some research needs here. We need fundamental interdisciplinary research for all of these processes. Model systems and modeling needs to be studied. Durability is not clear. Long-term studies is not clear. Demo projects. Someone yesterday talked about demo projects. Yes, for the love of God, we really need demo projects. If you're not going to put these in small projects, we'll never put them in large projects. So we have to work with industry and we have to find ways to de-risk new technologies. That's something that I'm working on. LCA and TA is needed. Actual quantification of carbon, Dr. Banthia talked about it a little bit. That's a challenge. Synergies and interaction, integration with other technologies are well understood. Most important, actually almost as important as research, specifications need to be updated, standards need to be updated, education needs to happen, the workforce needs to be developed. None of these new technologies will take off if the people on the field don't actually want to work with them, if they're a pain to work with. So all of these need to happen concurrently as well. So I'd like to thank all the agencies that have been kind enough to fund our work. I'd like to thank the audience and also my PhD students, etc., for doing this work. So before I end, just 1 second, there is a QR code there. If any of you are interested, please scan the QR code, enter some information. It's for a project that we're doing that will come in useful. With that, thank you very much. And I'll take any questions.
Thanks, Pranoy, for keeping up with the time. Now we have time for a few questions. Go ahead.
Thank you, Professor, for the nice presentation.
Mike, you can use this.
Thank you for the nice presentation. In one of your slides that you said that you're doing beneficiation and together you are pumping CO2 also. So, but how the carbonation you are expecting there, because if there is condition, something like humid and what's going on there? So what is the degree of carbonations happening there? I mean,
sure, that's a great question. So I'm not doing this, okay? And I'm not doing it because it's a very scary thing to do, okay? My lab is not really set up in such a nice way. So this is very high energy grinding, etc. If I'm putting CO2 in the system, I'm terrified of a leak. I'm not doing it. Others have done it, including at scale, okay? And the idea, no, this is not a very moist system. There's actually some amount of moisture, and you can actually optimize the moisture for CO2, okay? With respect to the CO2 uptake, now this is an interesting question. Most materials will uptake zero CO2, okay? If you take something like a clay, a mine tailing, or a basalt fine, these are not materials which have any reasonable amount of calcium or magnesium. They won't uptake any CO2. But if you take things like steel slags, okay, or recycled cement paste, maybe, you know, there are some other materials which have olivines, things like that, which high calcium and magnesium content. They are the materials which uptake CO2. So I work with some of these companies, and the CO2 uptake that we see, as I said, for some of the materials which are non-reactive is zero. The highest CO2 uptake we've seen is about 22%, and that's really for RCP. For steel slags, we see about 12 to 16%, and for some other materials, somewhere between 2 and 9%.
Yeah, so very insightful presentation. I just wanted to ask this, you told about mechanochemical activation or thermal activation of, say, waste sources. or any kind of clays or alternative sources. But suppose if we optimize all your parameters, but what is your comment on the variability which we get from the sources? So for each time, do we need to repeat all, or can this be standardized? What is your take? How can we proceed to standardize these things?
This is a really, really, really good question. It's something that we are very, very concerned about as well, okay? For a lot of these materials, we find that it is a factor, okay? So our suggestion has generally been that these new technologies will work well when you have a large volume source, okay? So some of the basalts that we're dealing with, they have about 30 million tons or so, and the material is fairly uniform, right? So on something like that, it works. But if you have 100,000 tons of material and then the next material is highly variable, we are seeing that, you know, some changes, for example, in particle size or in alkali or in calcium content will actually cause changes in the products as well. So there is a new standard, ASTM-C 1912, that allows the use of things like mechanochemical activation. So any new material that you have to make has to meet that specification. Now the point is for you to do it in a reasonable manner, and there are, by the way, also cost considerations, CO2 considerations, etc. We found that, you know, it's very energy intensive, but others have been able to reduce the cost, CO2, etc. But you really need a consistent source for this to work, at least initially, right? Same with the thermal activation, like small amounts of calcium and alkali, for example, can really change your final product. So this is not something I would recommend if you have a small amount of material. Great question.
Thank you.
Yeah.
We can take one more question. Amit.
Thank you for the presentation, Professor. My question is regarding using different SCMs is a good option to reduce the clinker factor. But the issue is how do we manage in case of real conditions? If we have more SCMs, we have to deal with them, the storage part, as well as managing them, blending them together along with the clinkers. So most of the cement companies, they need to work on that. So what would be the best way to settle on that?
So there are two ways of adding SCMs, right? One is that you add SCMs directly to the cement itself, right? And the second is that no, you don't add to the cement. The cement you produce has relatively low SCM, but then you add it when you're making the concrete, right? Different places use both of these. For me, both of these have to be really established, but we really have to stop making just cement without SCMs. India is great. We have a lot of PPC. In the US, for example, we still make a lot of cements which don't have much SCMs. So a lot of countries first have to move on where even your base cement already has something like 30% SCM. That's a good start. And two, yes, you're right. I mean, you know, there are issues with silos, things like that, but as long as we can show good properties, reasonable cost considerations, then people will continue to use SCMs. And this is where things like education becomes very important, right? But yeah, managing capacity is important. And this is where, you know, you really need your SCMs to do well. A lot of SCMs, for example, do well on reactivity, but they have issues with finishing, okay? So then contractors don't like this material because it doesn't finish well. We have issues with workability, things like that. So all of those have to be solved. So there's a little bit of a perception issue as well. And yeah, you do have to invest. So again, the same thing that I mentioned before, if you're just having 35 different SCMs, but all of them have 100,000 kiloton, it's not so useful as having some SCMs which have lots of capacities. But of course, the answer also varies geographically.
Working at small scale instead of looking at large scale, because that will reduce the transportation cost using the locally available material.
Yeah, for sure, right? I mean, this is where the trade-off happens, right? If you can really use things where you make them, that is fantastic, but that's not always possible. So,
Yeah.
But I agree with you.
What is his name? Hello, yeah. See, in India, like you can see more than 6,000 to 7,000 ready-mix plants operating each city. You take Bangalore, more than 350 RMC plants. Hyderabad, 400 RMC plants. All the RMC plants have 3 to 4 silos. So they are comfortably able to blend either GGBS or fly ash. Even certain plants have even silos for micro fine products, microsilica or micro ultrafine GGBS. So the blending is phenomenal with all the RMC plants. So we don't have a problem. Maybe US there may be a problem, but availability of the the SCMs in India is there. The slag is available, fly ash is available, microsilica is available, ultrafine GGBS. These are all available, and many concretes are being made with triple blend. Even in cement sector also, people are now making slag cement. then PPC cement, then composite cement, of late LC3 cement. The capacities are also increasing. So in India, I don't find a challenge for blending this material.
Thanks for clarifying.
So-
Last question. Yeah.
It has become practically difficult to get OPC even for laboratory purposes also in India. You are very right.
Just to add on to that point, right, I think that's actually better than the US because we definitely have a bit of an availability issue, a little bit of a quality issue, and many of our silos are 2 to 3, not 3 to 4. But yeah, the biggest issue is just proper availability of materials.
India, it's like
Nice.
Yeah, last question. Please
Yeah.
feel free to discuss after the session. Yeah.
I have a question related to reactive silica in fly ash. We have a standard IS 3812 part 1 in India. There is a test called reactive silica test which says minimum reactive silica should be 20%. There are many methods. The method given in our code is a little bit complicated. So many chemicals, so many things, and you have to use photometer, optical density, all these things we have to do. But when we use fly ash, we use 320 minimum fineness, 320 mid square per kg minimum. But we have ultra fine fly ash coming with different fineness and all. Exactly, we will not be knowing. We get a strength due to particle packing or anything. The physical properties are always there, mechanical properties. But is it really how much it is important to determine reactive silica and then use the particular fly ash? I want to hear from you on this.
Okay, I will give you an honest answer. Please, if somebody likes that test, don't feel bad. I think it's a nonsense test, okay? It's just my opinion. I know a little bit. Tests which generally determine things like reactive silica, reactive alumina, or under some conditions, calcium hydroxide consumption. These are not very good. There's almost no data that shows that they correlate with real life performance. If you want, actually one of the better tests is the Indian lime strength test. That's a much better test that I would suggest rather than your reactive silica. But if you're not interested, just run an R3 test. An R3 test is extraordinarily simple, okay? I'm happy to give you the information. Run an R3 test, and you know, if you don't want to run it in a calorimeter, just run using bound water. It's as simple as it gets, right? And you can fairly easily determine it, and we have run it on a number of fly ashes, and you can actually see the effects of things like fineness, etc. The second thing, if you're not so interested in running that, just run a bulk resistivity test as well. There was a presentation here yesterday talking about bulk resistivity, and that's something that will help better as well. Honestly, better than reactive silica, even strength is probably a better thing to measure. Thank you.
Let's thank our keynote speaker, Professor Prannoy Saroni, one more time. So next presentation is on development of geopolymer concrete for direct construction application by Sabhavat and Prabha. You have 10 minutes, 1 minute for Q&A.
Good afternoon, sir. Good afternoon, all. I'm Jagan, PhD scholar from Department of Civil Engineering, NIT Trichy. So today I'm here to present a novel mixed design strategy for ambient cured geopolymer concrete, which is directly applicable for field construction without requirement of oven curing and high molarity. So these are the outlines of my today's presentation. Before going to the novel mixed design strategy, I would like to brief you what exactly the project. So we all know that we have economical and sustainability challenges with conventional concrete. Geopolymer concrete is one of the sustainable and economical approach that we can replace cement use. But still we have a few flaws, challenges, and limitations of geopolymer concrete. For example, it needs a high temperature to get the higher strength, and it needs high molarity. And also, we don't have a standard mix design for geopolymer concrete. So in my project, I wanted to produce a geopolymer concrete at ambient temperature and I wanted to develop a standard mix design for the ambient cured geopolymer concrete. So these all are the object mainly to develop a ambient cured geopolymer concrete and to develop a standard mix design, and also to understand its sustainability aspect in terms of carbon emission. Coming to the methodology consists in 3 design stages. So design 1 is completely selection of various parameters required for the water content, required for the mix design strategy. For example, selection of water content, it means solution content for geopolymer, and also selection of slump, and also selection of water cement ratio versus targeted strength, and selection of aggregate proportions, and also selection of solution silica modulus, pH, and viscosity. And design 2 is completely experimental work from casting to the testing. And design 3 is validation of mix design from the experimental work. Coming to the parameters required for the design, here slump, water cement ratio, and targeted strength and total water content is selected from the ACI standard. And selection of aggregate proportions are used from the DIN standard, and selection of chemical composition is fixed based on the Indian standard 17451/2020. Here solution is playing a very important role. It's a neutral grade sodium silicate with high silica modulus and high pH and high viscosity. And solution silica modulus is 2.92. And here is the mix design table and mix ratio table and few samples after testing. Coming to the validation of mix design. So here slump, like I have selected a water cement ratio from 0.4 to 0.8 from the ACI standard. And I have got the slump from 120 to 150. As the solution content is increased, slump is increased. And here I have the 7 days, 28 days, and 56 days compressive strength. As the water to cement ratio is decreased, strength is increased. Coming to the comparison, the targeted strength as ACI provided is like 50 to 19. And whatever the result I got at 28 days is closely matching. And the R square value between the obtained strength and ACI proposed is like 0.9. It's like around 0.96. And in terms of sustainability, for all the water cement ratios from 0.4 to 0.5, it comes under the sustainability. Coming to the conclusion, like I have developed a ambient cured geopolymer concrete and mixed design strategy, and all the ratios comes under the sustainable. Thank you all.
We have time for a couple of questions. Yeah, Shubham.
So, nice presentation.
Thank you.
So, how much slag, what is your precursor? How much is fly ash and how much is slag in your system?
See, those things I have provided in the paper. Like I fixed fly ash to GGBS percentages based on the trial mixes. It varies from, like I have started from 100% fly ash and 0% GGBS. I have tested it, and I have increased the fly ash. I have decreased fly ash and increased the GGBS. Likely it's like 70-30, 50-50. So for different water cement ratios, there are different fly ash to GGBS ratios.
Okay, so for raw mix where you don't have any GGBS, did your concrete set, because you are talking about ambient curing, right?
Yes.
So did your fly ash based geopolymer, what you are saying?
No. It's fly ash GGBS based.
No, you have one mix with 0% GGBS, right?
There I have got 19, which is like.
How much time it required for setting?
You're talking about 0.8 ratio, right?
You have mixed there, 1 second. 80, 20.
See, 0.4 fly ash is 60%, GGBS is 40%.
Okay, so basically you have started with 20% of GGBS and gone up to 45.
Yeah,
right?
I have started with 10, but at 20% GGBS, I got the strength.
No, that's okay. Now the question is, with this high GGBS content, did you observe any cracks? Because this high GGBS shrinkage will be there. What is your take on that?
Like, I didn't observe any cracks. Once you check with the specimens.
Show your specimen back.
Yeah. Those specimens are after testing.
Okay, that's why it looks very.
Yeah.
Okay.
That's what I mentioned, tested specimens.
Okay, I think
Okay.
if you want to discuss,
Yes,
please
yes,
feel
we'll talk
free
later.
to discuss afterwards. Thank you so much.
Thank you, sir.
Yeah. So now our next talk is on characterization and reaction kinetics of carbonated wollastonite blended cement composites. The speaker is Dandu Prasida. Yeah, please. 10 minutes.
Where is it? Where is the presentation?
हमारा presentation नहीं है मैम.
No, it's not mine.
मैम
Yeah,
का
there is no
presentation.
presentation, not mine. To ma'am, she told she'll be sending. Yes, sir, that is better.
There is a presentation on mixed design strategy for geopolymer binders incorporating fly ash with varying reactivity. Yes, you can go ahead. Then we'll figure it out. Yeah.
Good afternoon, everyone. I'm Pooja D. Prasad. I'm a PhD scholar of Professor KVL Subramaniam at IIT Hyderabad. So today I'll be presenting my work on mixed design strategy of geopolymer binders incorporating fly ash reactivity. So basically, geopolymers are we say like sustainable alternative since it does not have any clinkers in it. So it's a sustainable thing. So we have to find more alternatives for this thing. And then the major problem with today is like our previous speaker spoke about the mixed design standardization. That's the problem that we are not able to imply it to the field applications. So my effort is to make sure that try to standardize or come up with a more chemistry related approach to tackle the problem that we have with fly ash reactivity, because with the same fly ash, if the same fly ash has same oxide composition also, it might have a different amorphous content. So, but as of today, whatever the practices or whatever the mixed design strategy that people follow is either they add molarity, fixed molarity, or they go for the activator ratios. But yeah, so two different approaches. One is empirical, wherein people do trial and error by varying molarity, adding higher molarity, 8 molar, 10 molar solutions, or fixing up the sodium silicate to sodium hydroxide ratios and varying that. But we never guarantee a particular strength. So nobody considers the fly ash reactivity, because reactive content of the precursors play a key role in the strength and other properties. So I'll be focusing more on the mixed design procedure. So how I've arrived at this particular approach is that I've considered the precursor composition. I've analyzed the chemical composition of the precursor, because total oxide composition is not the reactive composition of the material. So precursor composition is the reactive part, that is the glassy part of the material. So first what I do is I've considered 95% fly ash and 5% slag, just to make sure that it sets at room temperature. Otherwise fly ash alone will not set at room temperature. To achieve the early strength as well as the acceleration, I've added 5% slag in my mix, and I've fixed the water to solids ratio of 0.21 and silica modulus, that we say silica to sodium ratio of 5 and silica to alumina ratio of 2, wherein I was able to achieve a little bit good workability as well as the mechanical strength properties to balance the alkalinity as well as the dissolution rates. And reactive silica and alumina was quantified using XRF and retooled XRD. So materials, I've considered 3 different sources of fly ashes. First, I've analyzed the oxide composition using XRF and slag also. And then for the same material, for all the 3 fly ashes, I conducted XRD, and I've separated the crystalline phases as well as the amorphous phases. So this is the formula which was developed by Dr. Bhagat Singh and Professor K.V. Subramaniam in our team. So how exactly the reactive silica and reactive alumina is calculated. So quartz, mullite are the crystalline phases that is present in the fly ash. So that separated by the oxide composition that was available from the XRF, this thing. So if we subtract the total reactive silica from the oxide composition, the total silica from XRF minus the quartz, which has silica content, minus the mullite content, we get reactive silica. Similarly, mullite has alumina. So separating that from the XRF oxide composition, we get the reactive alumina part. So based on that, that become the basis for me to supply the additional silica as well as the sodium required in my mix. So that is the basis for my mixed design approach. So those are the reactive percentages present in the 3 different fly ashes. So compressive strength, I've considered both accelerated curing as well as ambient curing. For accelerated curing, I've cured at 85 degree for 1 day, and remaining I've cured at ambient temperature just to achieve that heat, this thing. And based on the reactivity, I've considered for 1 to 28 days age. And we can see that higher the reactive proportion in precursors, higher is the strength during the various ages. Also, we can note that because of the accelerated curing, 1 day strength achieved almost close to 28 days. At the same time, I've considered ambient curing also. So in this particular case, we can see that 1 day strength is not predominant, but as and when the age goes through, by 28 days, it is almost normalized to the 85 degree accelerated curing. Even here, higher the reactive percentage in the precursor, higher is the strength that we can note. So this is an precursor-informed approach, is basically to tackle the lack of standardization, and also in order to minimize the sodium hydroxide that is going into the mix by, in order to reduce the efflorescence problems and all that. Also, it is a scientific approach where we tackle the chemistry, because the major amorphous glassy content is the plays key roles in dissolution as well as the polymerization. And also, we can say that higher the reactive silica and alumina, better is the performance based on the results that I've got. So these are the references, and I'll be happy to answer any questions. Thank you.
So we have time for now a couple of questions.
I didn't measure pH. Molarity is 3.54, so.
You have used both the solutions, like
sodium silicate as well as sodium hydroxide, yes.
Okay. Then what is the pH? pH is important for dissolution of aluminosilicates.
Yes, but
Then
I didn't measure, I need not measure pH.
You had some results, no? pH?
I've not measured pH. In my results, I've not measured pH.
Maybe.
It's a highly alkaline system because I have molarity. All the sodium is supplied by sodium hydroxide. With minimum sodium hydroxide, I was able to activate the solution and the strength. So, yeah.
Go ahead.
Yeah. So regarding pH, anything it will be more than 14 only, definitely, because we are going more than one normal, so definitely it will be more than 14. Now, nice presentation.
Thank you.
Coming to your precursor informed approach, I think this approach for the geopolymer community, we should try to adopt and encourage and standardize also, because there is lot of misconception for geopolymer that it requires very high molarity of
True.
NaOH, and the thing is people try to supply additional NaOH to dissolve their fly ash, which is I feel which is not correct. You supply only sodium hydroxide, the amount which can be
Helpful
which
for
helps in
dissolution.
reacting whatever proportion which can be reacted, right?
Yes.
So it's important to take the glassy content into consideration.
That's what I'm trying to
Okay,
establish.
all the best.
Thank you.
Go ahead.
Thank you for your presentation.
Thank
I
you.
just wanted to ask, did you do any reactivity tests?
Yes, for precursors or after post test, post compression.
No, precursors.
Precursor, yes, I did the XRD, X-ray diffraction studies, and retweeled refinement.
He means reactivity tests where we are just what
No,
Pranay was
not
talking about.
reactivity test per se. I didn't
Okay,
do
'cause
that.
you're-
I've directly calculated the reactive silica and alumina based on the XRD and XRF data that I have. So in my fly ashes, the reactive silica, one of the fly ashes has 22.4% reactive silica and 15.25 reactive alumina, and goes on, all the three different fly ashes, based on the formula that we developed in our team.
Okay, no, it's just because you said varying reactivity, so
Yes,
that's why I asked.
I didn't do any reactivity
Okay.
test per se.
Okay,
Thank you.
Thank you so much. I think, thank you again.
Thank
We'll
you,
move on to the next talk by Mr. Vishwanath, who is going to talk on temperature controlled raft foundation concrete for tall structures.
Good afternoon, everyone. I thank ICI, ACECON 2025 team for allowing us to present this paper. This is more on how practically we were able to achieve whatever we have spoken till now, durability and sustainable approach in mass concrete. And I have a case study which is related to AP, Head of the Department and Secretariat building, which is around 185 meter tall, a 42-story building. So it was done in 2018 end and 2019, early 2019. We all know mass concrete is defined as any volume of concrete with dimensions large enough to require that measures be taken to cope up with the generation of heat from hydration of the cement and attendant volume change to minimize cracking. So major issue is in the mass concrete, like rafts or major pours, there are two issues. One is the heat of hydration which is getting generated and the relative cracks getting developed because of differential temperature at any given point of time between the core and the surface which is exposed to ambient temperature. So this increases, this possibility increases as the depth of the foundation increases. So the main criteria for mass concrete requirement is durability, not the strength, because ultimately foundation is the last component of the building or the structure which is subjected to load. So we should take advantage of this and try to make foundations or mass concrete as durable as possible. So how do we do it is a challenge, because we generally notice that for large volume of concrete and concrete structures, the core temperature can go as high as 80 degrees. And if we don't take measures to control it, and more importantly, the differential temperature between the core and the exposed surface, which is the primary criteria for cracking and making the structure not durable. So that is the whole idea, and it's very difficult to design the structure without cracks. So your reinforcement detailing and your construction joint detailing is very, very complicated. So this, how did we achieve, is what I'm going to briefly dwell upon. So this is the view of AP, HOD and Secretariat towers. It is 5 towers, T1 to T5. T1 and T2 is being built by Shapurji, T3 and T4 by L&T, and T5 by Nagarjuna. So T1, T2 were the first concrete which was carried out, and it is the dimension you can imagine, 52 meter by 52 meter by 4 meter. So depth of the foundation was 4 meters. And because of the complex detailing of construction joint we can provide for this large volume of structure, we decided to do it in one go. And it was around 11,000 cubic meter of single pour. And at that time, this was the largest volume of concrete which was done for an RCC structure. How did we do? The planning started from 4 or 5 months ahead of what we were supposed to do. The first draft was supposed to be done in December. So we started from July, August, and Dr. Manu Santanam from IIT, Chennai, and Dr. Nagendra, who is with us, who is also the co-author of this paper, helped us in designing the mix. And we carried out a lot of trials, and mock-up was also done to verify what is the actual temperature which is getting developed at the core of the structure. The pour highlights, size of the raft, 52 by 52 by 4 meters. Total quantity of reinforcement, there were 7 layers at bottom of 32 mm diameter and 7 layers at the top. And in between you have skin reinforcement also. So total quantity of reinforcement steel, close to 1,250 metric tons. Concrete, quantity 10,800. Grade of concrete was M45. And we decided to reduce OPC as much as possible to reduce the heat of hydration. There are a lot of empirical formula available to calculate and estimate the heat of hydration. But that is not for Indian cements or Indian condition, but we had a fair idea by using that. So we decided that we'll go with 60% of GGBS and 40% of OPC. And that was the largest replacement of supplementary cementitious material at that time. So we had to have a lot of logistics, we have to carry out a lot of designs, and how do we store the material? That was one of the questions, right? So there were a lot of infrastructure involved to carry out this type of pour. Cement requirement was 2,000 tons. GGBS was higher because it was 60%. So it was 2,800 metric tons. And more importantly, we need to have water because they didn't allow us to use ice. They were very skeptical about the source of water which is used for preparation of ice. So they wanted only water. They gave us the river water, and storage of such huge volume of water was also a challenge. So instead of ice, which would have further helped us to reduce the temperature, we used to go for chilled water because you don't get that reduction. Minimum temperature you can get is only 7 to 9 degrees. So that was a constraint. Plant and machinery for this large pour. We have 5 chiller units, 5 batching plants, total installed capacity of 360 cubic meter per hour, 8 concrete pumps were used, 6 boom placers, and 2 line pumps. And approximately 200 people were involved in each shift. Execution was done very methodically. The most important thing was to reduce the temperature at the placement as much as possible. But unfortunately, we cannot go beyond or less than 28 degrees. And temperature of concrete developed during the hydration process was measured using thermocouples. So we used 3x3 matrix, 9 thermocouples at 3 different locations were used at top, middle, and bottom. So these were the elaborate sampling process which was arrived much in advance because infrastructure is huge. So this was discussed with the authorities and we arrived at this sampling. So we did for strength and we did for durability aspects also. This is how exactly the site looked. And you can imagine the depth of foundation, 4 meters. Normal chairs were not possible to be used. So we used channels to support the steel layers. This is 3x3 thermocouples at 3 different locations and readings were mapped. We took all the control measures at site. Every batch of concrete was controlled and all temperature and all other parameters were measured. So this is one of the important aspects I would like to highlight. Normal curing doesn't work in mass concrete because the differential temperature we need to control. And once you put water, the differential temperature will go up. So instead of conventional curing, we need to go for insulation. So how did we do? We completely sealed with curing compound, then a layer of LDPE sheet, then the thermocol 50 mm, and then again LDPE sheet. So this insulated the entire surface. So this was the reading. We got red indicates the maximum temperature and it started to come down. These are the various temperatures which were developed at each thermocouple locations. And these are the results out of large amount of sampling we have done. Every parameter was within the limits. I just run through this video which is very interesting. You can see the magnitude of the work. It's hardly 2 minutes. So at that time, this was the single largest RCC pour done in India. You can imagine the amount of machinery and the manpower deployed and the logistics and the planning. Where? No issue. Where do we? Conclusion, the most important aspect is the placing temperature has to be controlled. The differential temperature between the core and the surface at the top has to be controlled to avoid differential settlement, differential thermal stresses. And use of supplementary cementitious material to the extent possible gives a very good result. And the curing, instead of conventional curing, you need to go for insulation so that the temperature differential is minimized. And we could achieve a minimum of 4 to 8 degrees temperature gradient. So it was a very commendable effort, and we did not see any thermal cracks. So this insulation was kept almost till every temperature monitoring was reduced to ambient temperature. Thank you.
Thank you so much. We have time for only one question. Yeah, go ahead.
Hello, sir. Excellent work. Fortunately, I was part of one of the pores that happened in 2012. It was 7,500 cubic meters at one pore. It was a blast furnace foundation in NTPC Nagarnar. So I do not remember the method of curing that time. But the question is, instead of providing the surface coating for insulation, did you explore the possibility of controlled curing through water with a controlled temperature? I mean,
ideally you should have left some pipes inside. That's what you mean to say, right? Yeah. But external water is extremely difficult to control. We have learnt it the hard way in one of our projects, 22 meter by 22 meter by 2.5 meter. We did it with conventional curing, and we had a lot of thermal cracks through and through, and we in fact ensured the monolithic action by grouting with epoxy. Okay. So from then on, we have done a lot of pores, almost some 10-15 mega pores. We have done insulation, and results are excellent.
Okay, thank you.
Okay, thanks. Thanks for sharing your work on very interesting, challenging projects. In the interest of time, we'll move on.
Thank you.
So next presentation is by Prasida Dandu on characterization and reaction kinetics of carbonated wollastonite blended cement composites. 10 minutes. But feel free to interact with the speakers after the session. Okay. Thank you.
A very good afternoon to one and all. I am Prasida. I am working as assistant professor in VNR VJ IIT Hyderabad. So I'm here to present my work on characterization and reaction kinetics of carbonated wollastonite blended cement composites. So contents are of this. So we all know the concrete is a composite material consisting of the aggregates, the cement, water, superplasticizers and all. And with the progress that has been happening throughout the world, this concrete is a material which is being used for development of any of the infrastructure all over the world. So the volume of the concrete worldwide was estimated to be about 14 billion, and production of the cement was around 4.2 billion tons in the year 2020. And it is also been expected that population is going to get raised by 9.8 billion by 2050, and there will be also production of the cement that is going to be increasing as per the report published by the Global Cement and the Concrete Association. And cement industries, they are in a far way to just reduce in the carbon emissions due to the production of the cement by adopting many of the things like electrification of the blast furnace or using of the RDMs as fuels, etc. And as well, we could also able to see in USA and the UK, the part of the fly ash what has been getting utilized is also been getting reduced due to the shutdown of many of the steel plants over there, and their dependency on the GGBS has also been getting reduced. So as a solution to this, there are some natural materials that are being available which can actually be used as supplementary cementitious materials. So one such a material what has been explored recently is a wollastonite material. So it is a naturally formed mineral, so it can also be synthesized using some of the silica content and the CaO content material fusing together. So this part of a wollastonite is being explored in my study. So these are some of the statistics of the production of the natural wollastonite material country-wise. So as we could able to see in from 2023 to 2021, India being a largest producer of these wollastonite material. So this is a forecast of the wollastonite production, what is going to take place whole over the world. And if you could able to see in India is in a position to produce or to supply in a wollastonite of larger quantity, followed by China. And experimental investigation has been carried out in this by many of the researchers in past. The difference is like they have been using only the wollastonite as a material in concrete as partial replacement to the cement, but what they have been reporting is like the optimized amount of the wollastonite was in between 15 to 30%, depending upon the size and all. So in my investigation, what we have done is we have carbonated the wollastonite. As we all know, the wollastonite is a calcium-rich material, calcium silica-rich material. So there we had seen a thing like this part of a material can able to absorb the carbon dioxide and could able to also serve in the purpose of the carbon sequestration thing. So this is a part of a study what has been carried out. And there is also a limited literature on the carbonation of the wollastonite, because when we have seen only Frank Wenifield, one of a researcher from MPAS, Switzerland, he was been carrying out whole of a research. But the thing what we have observed in there is he have been carbonating whole of the wollastonite for 24 days under different varying temperatures and pressures. So what we have done in our case is we try to carbonize the wollastonite to a minimum period of time, like in 4 days, 7 days, and 10 days. Likewise, and we could able to observe in the amorphous silica is getting being developed, where the crystalline silica is getting transferred into the amorphous silica with the amount of the carbonation that is being taking place. So these are the materials what are being used in the experimental investigation. The wollastonite, which has been provided by the Allchem India Private Limited. So this is one of a company which is largest producer of this wollastonite all over the world from India. And we have used a standard sand, apart from which we have also used the super plasticizers like SP430 in order to control the workability condition of the concrete mixes that has been formulated. And the wollastonite, we have got it in different sizes, but the part of the experimental work what is being shown here is being confined only to one particle size of 43 microns. And what we have done is we have adopted a water to solid ratio of 0.5. That means we mixed in the solid content of the wollastonite with the water, and which we have spread it on porcelain pan of 12 mm, and we have put all of those things in a desiccator, and all of the desiccator has been filled in with the carbon dioxide. So after each of a day, like at intervals of 3 days, we have tested how much is the carbonation sequestration that has taken place, because we don't have a carbonation chamber at that time, but now we do have it. So these are the tests what are been conducted. So we have tested it for the compressive strength and the flexural strength, wherein we have used the code ASTM C305 by mixing in the material in the ratio of 1:2.75. So we have replaced the cement in the range of 5 to 50%. And the compression test and flexural strength test was conducted, and apart from which we have also conducted the microstructural studies, wherein we studied the mineralogy in terms of XRD and also calculated the bound water and the portlandite content from the TJ analysis. So these are the results what are being shown. So if you would able to see in the 35% was showing, replacement was showing the maximum compressive strength for the carbonation sequestrated wollastonite incorporation as partial replacement to the cement, and this is a flexural strength. So for the same mix, we have got these values which are about 5.8 MPa, and it has been noticed that the compressive strength has increased with the replacement of the cement only up to 35%, but this is not like a thing very significant, but we are been trying to carbonate the wollastonite to much extent so that we could able to see in like partial replacement of the cement is going to be increased by thereon. And from the XRD also, these are some of the results what we have seen, wherein the part of the Portlandite that has formed has got reduced up at the percentage replacement of 35%, and from there on it has got increased again. So this is the TJ analysis what we have carried out, and from which we have also determined the bound water content as well as the Portlandite content with the formulas what are being listed out in the handbook what is being published by Lothenbach Barbara of Empire, Switzerland. So she guided us in this whole of the project. So this is a part of a work what has been conducted up to now, but there is a way forward to take it further. And this is a future scope what we are been aiming at for. So in order to extend this, we need to actually optimize the carbonation conditions of the wollastonite to make it more sequestering the carbon dioxide it is going to be exposed to. So that is a part of a work what actually need to be carried out further by varying the parameters such as the temperature, the pressure, the humidity conditions and all. And hence the carbonated wollastonite serves as a supplementary cementitious material by converting whole of the crystalline silica into the amorphous silica. So that is a part of the thing what is being to be done for. Thank you.
One quick question. Yeah, please. Here.
How to characterize this wollastonite material? Are there any standard for this material?
So there is an XRF what we have conducted to determine the first the chemical composition of the wollastonite, sir. So from which we have also conducted an XRD to determine how much of the crystalline phase of the silica is present and amorphous present, but the amorphous phase of the silica that is been present is very, very low, sir. So what we have done is again we carbonated it to certain days, adopting the standard temperature, humidity and all of this, sir, and the pressure that has also adopted is of 2 bars. So we have taken it for every 3 days, and after 14, likewise we have taken out the material and we have tested again for the XRF, sir, XRD, and we have seen it to be like the crystalline phase is getting converted into amorphous phase, sir. So that is a little work we have done.
If I want to use it, wollastonite material in concrete or mortar, how do I know that this material meets the requirement? I can't do XRD, XRF every other
Yes,
day.
sir. That's why we have been in the process of optimizing the parameters at which all of the carbonation sequestration is maximum to its extent, sir. So that is a way forward what we are carrying out, sir.
Thank you.
Thank you.
Future studies.
Yes, sir. Yes,
Thank you so much. Please feel free to discuss with her later on. Let's thank our speaker one more time. And the next speaker is Umesh from IIT Madras, who is going to talk about carbonation-induced corrosion of steel in concrete with fly ash and limestone calcined clay. 10 minutes.
So, hello everyone, myself Umesh Shule, I'm from IIT Madras. I'm working with Professor Pillai on the topic carbonation-induced corrosion of steel in a concrete with low clinker systems. Typically, today I will be discussing the results on fly ash and limestone calcined clay based concretes. So why it is important, why the durability aspects of these new low clinker systems are important, because to confidently use these low clinker concretes, we require comprehensive information on their service life and how they perform in the CO2 exposed environment. As we know that construction industry account for 37% of global CO2 emissions, so the use of cement is highly contributing to this factor, and we required SCMs to reduce the CO2 footprint. Hence, and the low clinkers are required. And there is a problem it's observed with these systems is that they have the lower carbonatable content and they lead to faster carbonation, which could lead to a coarsening of pore structure, and that may lead to even reduction of resistivity. And we don't know their exact performance into the corrosion characteristics of these. So that's why we required models to assess the carbonation resistance and also to design the structures by incorporating the durability which is exposed to CO2. So this study we done for the last 10 years, and we have observed that The LC45 system, which is made up of limestone calcined clay, has a very high carbonation depths, around 20 in the span of 10 years, which is a little bit alarming, because the typical cover of concrete can be 20 to 30 and which could be carbonated in just a span of 10 to 15 years. So the huge difference is observed there, and we have developed a model in which also it is concerning that in 30 to 35 years of corrosion, the concrete can carbonate and lead to corrosion initiation. So here there is a need to investigate the propagation phase in this condition, because the corrosion rate in the systems are not that high because of carbonation-induced corrosion. Hence, I have studied these systems in a different environment, which is already carbonated, and then I have calculated the corrosion rate in these systems. Where I have observed in OPC, that is actually the positive response is observed, where the carbonation has led to a reduction in the corrosion rate and in improved microstructure, which is also somewhat observed in the fly ash systems, but you can see it here in the LC3 system. This leads to a reduction in the impedance values. You can see it there, which is depicting that qualitatively that corrosion rate is increasing. So after that, I also calculate the corrosion rate in the systems. So quantitatively, we can see that the LC3 systems is having higher corrosion rate when they are carbonating. So this is a worry? So that is the biggest question. So to know that what is the factor behind that, I calculated the resistivity of the systems, and we observed that LC45 system, there is a reduction in the resistivity by 1/4, and there is an increase in the resistivity in the other two systems like fly ash and OPC, which is positive for them, but the negative for the LC3 systems. So the reason behind the decrease and increase in resistivity is interlinked with the porosity, and it is observed that the pores of LC45 is becoming coarser, but the OPC and fly ash, they are becoming finer. So this is also happening in the natural environment, because I studied this in the accelerated environment. So we have some specimen which was carbonated for 10 years, and that I studied the resistivity, pH, and of this system before and after carbonation. They show the similar characteristics, which is like that we can study the accelerated studies also to design the systems. So the pore structure of low clinker system is the biggest advantageous for us to reduce the diffusion coefficient and have the high durability. But after the carbonation, it is observed that it is coarsening, and that could lead to even increase in the diffusion coefficients and also the higher carbonation rates. You can see it here. So the lower critical pore dia can be beneficial to provide higher resistivity and the lower corrosion rate with respect to that system. So I studied different system with varying the water to cement ratio, and it is observed that if the water to cement ratio increases, the resistivity drastically drops down and also leads to increase in the corrosion rate, which will be problematic. And there is a move forward to go with the system that to use the lower water to cement ratio systems, which will be less than even 0.4 or 0.45. In that system, even after carbonation, the corrosion rate were not in a high state, which was in the low to moderate level. So on the parallel note, we developed the model in which we can estimate the propagation phase in the system, as we know that the corrosion rate is influenced by the internal moisture. So if we have a system with the lower internal moisture, the corrosion rate will be lower, and we'll get the more propagation phase. And you can see that if we maintain the lower internal RH by less than 75%, we can get even a 30+ year of propagation phase in these systems. And moreover on that, we developed the nomogram is in developed, which can be used by practitioners to design this type of system, which also accounts for the propagation phase in their service life. So on conclusion, we required high resistive systems even after carbonation. That can be done by using lower water to cement ratio. Increasing cover depth is always beneficial, and lower internal moisture is at most required for the systems to provide a good durability. So overall conclusion is that yes, steel carbonation is a problem, but we can mitigate it by using the refined mixes, and yeah, 30 plus year of service life is also possible if the moisture level inside the steel concrete is lower than 75%. Thank you.
Thanks, Umesh. Time for one quick question, if anyone has. If not, we'll move to the next presentation. Thanks again. By Iqbal on early age hydration kinetics. So I think this presentation will be scheduled later after the lunch, it seems. So thank you again for attending this.
Okay. Thank you so much. I invite Engineer Girish, sir, Chairman of ICI, to do the honors. So I extend my gratitude to Dr. Piyush Sali, sir, for being the session chair. Thank you, sir. Now I invite our keynote speaker, Dr. Pranay. I request Engineer Girish, sir, to do the honors. Thank you, everyone. Now we'll break for lunch, and session 2 will begin in half an hour. Yeah, I think so. Lunch has started. Please join for lunch. And 3 o'clock, yeah. The second session will begin around 3 o'clock. We'll keep you posted. Thank you.
Yeah, you heard of particle density packing. We will show that to you immediately after lunch, how we
that affect concrete durability in general. Then we'll talk about what can be the ways for doing performance design of concrete with low clinker systems, primarily with three particular service environments. One is sulfate attack, one is chloride-induced corrosion, and one is carbonation-induced corrosion, because these are mostly talked about as far as durability design and control are concerned. So what are low clinker systems? I'll first, of course, qualify that my presentation here is only about low clinker Portland cement based systems. I'm not going for alternative systems which don't have Portland cement. So my talk is not featuring geopolymers, alkali activated cements, and so on. I'm only going to talk about Portland cements, low clinker Portland cements. So again, what is the extent of substitution that defines a low clinker system, right? That is something that we need to first consider before we really start looking at some of the critical aspects that affect durability of concrete. One is a boundary that we typically use in India is 35% for pozzolanic additives like fly ash and 50% for slag. Although, of course, slag cements permit up to 70% of cement replacement, but anything more than 50% of slag is generally qualifying as a high replacement or low clinker type system. In India, of course, we have these cements, Portland slag cement. We have composite cement, where we are crossing the boundary of 35% because the total replacement can be up to 60 to 65% of the clinker. And LC3, where we are looking at a blend which has 50% clinker content and substituted by a mixture of limestone and calcined clay. Right, in Europe, many cements actually fall in this category. Primarily among the slag cements, we have the CEM3 types B and C, and CEM4 type B, and also CEM5, which is a Portland composite cement. And because of that, there's a lot of combinations that can actually fall in this category of low carbon systems. Now, there are, of course, in concrete applications, sometimes we go much beyond what is there as a cement available in the market, because we want to optimize the design of concrete for the kind of engineering applications that we're looking at. For instance, when we're designing a raft, very often we can't stick to this 35% fly ash replacement anymore, because you know very well that to control the heat of hydration or to control the temperature development inside mass concrete, using a fly ash replacement of cement, more than 40% is often recommended to ensure that we have the right kind of control. So very often we deal with combinations, either binary, ternary, or quaternary, as far as cement is concerned, for concrete applications on site, right? So again, those are also qualifying essentially as low clinker concrete systems, whereas of course we also have low clinker cements in general. So let's look at a little bit at what the chemistry of these systems is. Of course, many of our replacement materials are pozzolanic materials, so they have reactive silica. And of course, slag-based materials have some degree of reactivity or hydrolicity of their own, which needs to be activated. So what this results in is, of course, a very high level of consumption of calcium hydroxide. When you're talking about pozzolanic materials like calcined clay or silica fume, a lot of almost entirely calcium hydroxide can get consumed, or almost complete calcium hydroxide. CaSH formed is quite different as compared to the calcium silicate hydrate in Portland cement systems. There's a lot of work on this, a lot of literature which shows the quality of the types of CaSH that are actually formed, higher degree of alumina substitution, and so on and so forth, lower calcium to silicon ratio, and so on. That defines these kinds of systems which actually form with low clinker binders. And again, just in terms of characteristics, lowering of the calcium to sulfur, silicon plus aluminum ratio. You have incorporation of alkalis and sulfates that happens within the CaSH, and also the distribution of your calcium sulfur eliminates could be quite different in the low clinker systems as compared to ordinary Portland cement-based systems. Ionic strength of these systems is typically low, because when you're substituting cement, which is very rich in ionic species, with alternative materials like fly ash or silica fume, there's a lot of binding of those ionic species that actually happens within the glassy structure. And further, since you're diluting the cement, the extent of alkalis that come into the system are anyway going to be reduced significantly. So when your ionic strength is low, it affects the conductivity of your concrete, right? Now, this conductivity, interestingly, is tied quite well to many of the durability tests that we do on concrete. We look at RCPT or electrical migration or chloride migration. All those kinds of tests involve the application of a potential difference. And that means the conductivity of the concrete will play a large role in the kind of results that you get with these kinds of binders. So that is one thing that also you need to keep in mind, that these low clinker systems essentially will have a lower ionic strength, leading to lower conductivity or high resistivity. And these chemistries, basically low clinker chemistries, are very susceptible to acidic environments. Okay. Now, if you look at it, carbonation also is essentially a form of an acidic attack, because your carbonic acid basically forms, your pH gets reduced in your system, and that leaves the steel susceptible to corrode. So when such environments are there, when you have low pH conditions, even in acid attack conditions, a lot of literature has shown that when you have very high degrees of replacement of the cement, you tend to have poorer performance. So there's definitely a vulnerability when you come to low pH conditions. So the other aspect which governs durability, one is chemistry, the other is pore structure, right? Now, low clinker systems have generally a very positive role on the pore structure. In terms of porosity, as compared to plain cement paste, when you have a low clinker cement paste, you'll not have that much of a difference. But the main difference will be in the critical pore size or the shift in the overall pore size distribution towards a more finer range, okay? So that's what typically happens. Now, what really happens here, while I've said that shift in critical pore size is only marginal, as the plot indicates, with time, basically, the densification of the pore sizes or shift to smaller critical pore sizes actually happens with Portland cement systems also. But what really happens in the long term is that the coarser porosity starts getting filled up with the pozzolanic hydration products, which leads to a much better densification of the overall matrix, which leads to much better pore structure in the long run. Okay? So what we need to consider is that many of these low clinker binders will lead to refined pore structures very early and will remain as such in the long term with the densification caused by the additional pozzolanic effects that are actually happening over time. The main effect that you see with these pozzolanic additives is the effect on the tortuosity. So think about a pore that is very straight inside the concrete. So water has to move through this concrete, it will easily go through that pore. But if the same pore or the connected pores are such that they are convoluted and they really have to travel through a long distance, then the transport of water and other aggressive species through the concrete will be severely restricted. So that's where the primary benefit of such systems come, in the tortuosity. Okay? So disconnected pore network happens in the outer CSH, and that is represented in many instances in the literature on durability by what we call as a formation factor. Now, the formation factor basically tends to normalize the conductivity of your overall system with respect to conductivity of pore solution. Remember, I talked about in the previous slide that the ionic strength is lower in low carbon systems or low clinker systems, because of which their overall conductivity is reduced. So when you do an electrical test, the test is highly in favor of these systems because you are basically lowering the conductivity such that your charge that is passing through your system is very low. If you remember, silica fume became very popular in the 1980s, around the same time that the rapid chloride permeability test also became popular. And both of them went hand in hand to popularize each other, so that RCPT became ingrained in the minds of any concrete engineers. At the same time, they believed that you could get low RCPT only with the use of silica fume, which is not correct. Fly ash-based systems can also get you low RCPT, but essentially what is really contributing a lot more than the pore structure there is actually the lower ionic strength. So when we want to define the pore structure, we also need to consider the fact that when we use electrical measurements of the durability parameters, we need to normalize the conductivity with respect to the pore solution conductivity, which is inside the pores. So that's where the formation factor is very effectively used as a means of characterizing a system that is more durable versus less durable. So formation factor, or I should not say more durable, I should say which has more disconnected porosity versus a concrete which has a more interconnected porosity. So the higher the formation factor, the more disconnected your pore system is. So when you use low clinker binders, very often you see that you get formation factors that are significantly higher than that of Portland cement. This is especially true when we use ternary blended systems with slag and silica fume, or ternary blended systems which have cements like LC3. Okay, so again, a lot of research has been done to show that the tortuosity is the defining factor when it comes to performance-based indicators like the non-steady state migration coefficient that we look at in the rapid chloride migration test. which is an often used parameter for durability control in many infrastructure projects, now even in India, right? Okay, so what are the durability issues that cause problems in concrete? We have, of course, leaching, which is a slow, time-dependent process with which the alkalis and the calcium-based systems slowly come out of your concrete. We have freezing and thawing. We have chemical attack, internal reactions like alkali-acid reaction or DEF, and corrosion of reinforcing steel. So all of these issues are affected, of course, by the chemistry of the paste system, as we described the differences in chemistry between low clinker binders and PC binders, and also the post structure of the concrete. So where post structure dominates are the problems like chloride attack and sulfate attack. Many of these, what has been seen through the literature that has been written about for quite a few years now, is that the effect of the post structure is much stronger than any other chemistry effect that you actually see. For instance, we talk a lot about chloride binding in slag-based systems. Yes, chloride binding is good, but at the same time, the positive impact of the post structure by slag inside concrete seems to contribute a lot more to the reduction in chloride penetration as compared to the chloride binding. Same thing happens with LC3 also. We see a very positive effect of LC3 on chloride-related problems, but there again, the effect of the post structure is much stronger than the effect of the chemistry. Where post structure dominates, as I said, chloride attack and sulfate attack, but certain types of sulfate attack like ammonium sulfate or magnesium sulfate attack can lead to acidic conditions, and there again, when you have low pH conditions, you do have problems associated with low clinker binders. Where chemistry dominates is essentially your carbonation, which is again one form of acid attack, and then your leaching. All of these will be dependent a lot on the chemistry. Okay, so low clinker systems are poorer when the chemistry gets altered, such as when carbonation happens or an acid attack, because there's not enough alkaline buffer or calcium hydroxide available to combat the external agencies which are interacting with the cementitious hydration products. So CSH gets directly attacked. And as I already said, there's considerable difference between the CSH formed due to PC hydration as opposed to what is formed through a pozzolanic reaction. So that also leads these systems to be more vulnerable in terms of direct attack on CSH. So the other aspect is the chemistry of the system can also affect the stability of the passive film. Now, we know that when steel is put inside a high pH environment of concrete, a passive film develops on top of the steel surface. And this passive film basically is a protecting layer as far as steel is concerned. When this passive film is broken, either by chloride penetration or by lowering of the pH, the corrosion of the steel gets initiated, right? So this passive film, the quality of the passive film can also get affected by the chemistry of these systems. So you know very well that since calcium hydroxide is going to get reduced in low clinker binders, the chloride to hydroxide ratio that is available on the surface of your steel, which is the defining factor with respect to corrosion initiation, will also get lowered. So that means your corrosion can get initiated at lower chloride thresholds when you start using low clinker binders. Now, interesting part is when you actually do corrosion studies, the performance of low clinker binders always comes out better than ordinary Portland cement. So this again goes to show that the post structure, that is the delay of chlorides reaching the level of the steel, is dominating much more than all these negative effects of alteration of chloride threshold. Okay? So that's why I said you need to look at the problem and understand what is the dominating mechanism that is affecting this problem. So durability design strategies that we come across should balance out this role of post structure and chemistry. It's not very easy because we only have a limited suite of tests to choose from, but we need to understand what are these tests actually representing before we actually carefully put together the parameters required for durable concrete. So just to give you some just give an example of chemical attack. So I've classified different types of chemical attack that are there. Some common features of these attacks. One is external sources. Basically, your chemicals are coming from an external environment, so they need some moisture in the concrete to be able to diffuse into the concrete system. Mechanism is mostly diffusion or combined with leaching or precipitation, depending on the type of material that is interacting. If it's an acid, there'll be much more leaching. If it's a sulfate, there'll be much more precipitation. And that ultimately leads to damage. So what is common amongst all these attacks is generally they'll lead to lowering of concrete pH to some extent. Sulfate attack, not always, but in some cases. Highly dependent on concrete permeability. As I said, since the source is external, it takes some time for this species to make through the cover zone of the concrete and come inside. And these are, of course, long-term phenomena. I mean, that's why studying these in the lab is often very difficult. Like sulfate attack, even the common test methods, you need at least 6 months to even come up with some idea about what kind of sulfate resistance a new cement actually shows. Some differences in these. One is leaching dominates in some cases, as I said, or precipitation dominates another. And when precipitation also happens, the solubility of the precipitates also seems to affect the rate at which your attack happens. In some cases, you may have precipitates that are highly insoluble and form on the surface and act as a barrier, right? That happens in carbonation of ordinary Portland cement. You have calcium carbonate formation on the surface that almost acts like a barrier, reduces the further ingress of CO2 to a large extent as far as OPC systems are concerned. In acidic conditions, the chemistry seems to affect a lot more than the pore structure. And damage, there are various forms you can see, expansion, loss of strength, and so on. So what do we do in durability design, right? One is, of course, we identify the correct exposure environment, right? We need to ensure that the kind of concrete we're designing is suitable for the kind of environment that we're designing it for, and what are the durability issues that are prevalent in that environment. We need to understand, obviously, the mechanism by which the liquids and gases are coming inside. Is it saturated concrete which is getting diffusion, or is it dry concrete which is going to absorb this material? All of those things need to be very clear before we choose the right test methods that reflect these correct transport mechanisms. And we also need to then set up limiting values for these tests. You might have always seen several different codes of practice or even specifications for certain jobs where they say that, okay, RCPT is the criterion for controlling the quality of the concrete. We need the concrete to always have a RCPT value of less than 1,000 coulombs charge passed. That's just one example. But several projects have their own different types of criterion by which they apply the durability. So once the idea is ready, then the concrete producer or the concrete engineer needs to perform mixed design studies to get the right combination. First, obviously, of workability. We need compressive and flexural strength, as the case may be, and obviously the durability tests in terms of the satisfying the limiting value or not. That's something that is done as a pre-qualification. And then these need to be applied on site, which often needs, obviously, setting targets on durability for the concrete production on site. Because we have to realize that on site, the variability is going to be much greater as compared to what you have in the lab. So definitely you need to set the targets for the actual site-related durability parameters, and that's what brings to the light the importance of acceptance criteria on site. And that is something which is still evolving with respect to durability as we try and understand what is the level of variation that is permitted in many of these tests. Right, so what are the different transport mechanisms? Just to give you an overall picture, you have, of course, sorption, permeation, diffusion, migration, wick action, absorption. All of these are different types of transport mechanisms, and the likely definitions are also given here, and the test methods that actually reflect these types of mechanisms is also given. Some test methods, as you can see here, rapid chloride permeability test is looking not just at diffusion, but also primarily is concerned with migration, right? You have your air permeability, which is basically permeation. Accelerated chloride migration is basically, again, reflecting some level of diffusion, but mostly it's migration. So some tests basically reflect multiple transport mechanisms. So you need to be clear as to what are these tests actually going to show you. So one example of how we define the material selection for different exposure environments is given in a book very long ago. This is about 50 years back by Professor Mehta. And this talks about a seawater column standing in seawater, right? So we have 3 different environmental zones within this column. One is the completely submerged zone, which you find right under the low tide level. Then you have the tidal zone, where you have the zone which is basically subject to the tides. At the same time, this is the zone which is also subjected to splashing by the waves. So this is obviously the most critical zone, what we call in IS 456 as the extreme environment, okay? And of course, you have the atmospheric zone where the seawater does not come directly as a spray, but you can have chlorides getting transported to that by the moisture in the air. So all of these require, of course, the choice of different types of permeation mechanisms, or transport mechanisms. When you are in the atmospheric zone, there is some sort of diffusion happening and some sorption. There's diffusion and permeation happening in the submerged zone. The difference being, in the atmospheric zone, this diffusion is happening through a partially saturated system. In the submerged zone, this is happening through a completely saturated system. So you need to, again, differentiate what is actually going on there. And then, of course, the tidal zone is where you have a combination of several different things. You have diffusion, sorption, wick action, and permeation. So let's now look at these three problems that I talked about initially, that is chloride, carbonation, and sulfate attack. What are the different mechanisms that are associated with these problems? So if you consider chloride-induced corrosion, you have, of course, saturated state diffusion that is happening in your system. You have liquid permeation, as I showed you here in the submerged zone and in the tidal zone. If there's sufficient water in contact with the system, there'll be water pressure, and that will drive more and more of these chlorides into the concrete. And then you have migration, which is not really happening in this situation, but it may happen whenever there's some potential difference or something which is created because of the kind of engineering application that you're dealing with. And of course, you also get drying and wetting and sorption happening in the tidal zone. So altogether, if you really look at it, it's a very complex environment. Similarly, for carbonation, you have partially saturated state diffusion happening, gas permeation. Carbon dioxide is a gas which permeates through the concrete, higher pressure of the gas on the outside, lower pressure inside concrete, so that will drive further intrusion of CO2 inside. You can have liquid permeation, but why liquid permeation and carbonation? Because after carbon dioxide goes in, you still need moisture to drive corrosion. Without moisture, corrosion cannot happen. So even that is a mechanism that you should consider as far as carbonation-induced corrosion is concerned. And finally, drying and wetting, which is a realistic possibility in most environments, most outdoor environments. And then you have sulfate attack, which basically involves penetration under pressure of liquids from the soil or from the groundwater into the concrete. That involves permeation. You can have diffusion again because sulfate is higher in concentration outside, so it will diffuse through the concrete. You have wick action and sorption. When the concrete basically dries, it is able to take in a lot more sulfate. So that's why very often you see that sulfate attack is especially greater in the zones which are at the interface of the air and the soil or air and the moisture. And drying and wetting again, just like any other situation. So now, if you really consider all of these durability mechanisms are driven by so many different factors, right? So let's take each one of them separately, and how should we define the durability parameters to be controlled in these environments is something we need to look at. So again, just to recall the story, we are here to live with low clinker concretes. There's definitely going to be an effect as far as durability is concerned, because durability is governed by the post-structure alteration as well as the chemistry alteration. So, and we decided that in some situations the post-structure dominates, in others the chemistry dominates. So what do we need to control? Carbonation, often termed as the biggest problem with low clinker binders. And that's absolutely true. There's more CO2 penetration that happens in these systems. Of course, very often an offsetting parameter is the positive influence on the post-structure that happens in these systems. You need to, again, balance out these two. So what do we need to measure in order to control the durability in such a condition? One is obviously the carbonation rate, right? Now, carbonation rate is not a test that everybody can do, but it's not a difficult test to set up, okay? Especially the accelerated carbonation. A lot of people are now using this measure to determine the ability of a concrete to resist carbonation. Penetration or carbonation depth can be measured with different types of binders, okay? Natural carbonation, of course, if you have time, and if you have several PhD students who will continue one after the other to take readings, nothing like it, but then that will take you a long time to establish anything. Your project will already be over by then. But of course, many of our projects will not probably get over. They have a tendency to keep on continuing for a long time. The other aspect, moisture penetrability, is obviously very important. In many cases, direct or indirect measure can be done. Indirect measure of moisture penetrability can be given by an approach like surface resistivity, right? That's again becoming very commonly used now. In Europe especially, where they are utilizing surface resistivity on site to determine the as-is condition of concrete that is in the actual structure, because that gives a good response with respect to the pore connectivity. And then you can also look at additional protective measures like an anti-carbonation coating, because we know carbonation depth is going to increase if your service life models with such concrete systems are simply based on the carbonation depth being equal to the cover depth. Then you have to make that additional protective measure to slow down the rate of carbonation that happens in these systems. Because carbonation rate is going to be high, you need to slow that down. So maybe additional protective measures are absolutely important. Now, when you go to chloride-induced corrosion, the chloride binding ability is something which we've talked about as the chemistry aspect, which I don't think, in my opinion, because post-structure is so dominating, I don't think it's very really compulsory to control. The moisture penetrability, either direct or indirect in terms of resistivity, I think is a good measure. to ensure that we get a clear sense of how fast the system will get saturated with these chloride-based environments. And again, durability indicator for the chloride itself, like non-steady state migration coefficient or diffusion coefficient. These are a little bit better as compared to your rapid chloride permeability test, which is a very quick test. I know, quick, it still is 24 hours. So you have to think about that, because you don't really get a quantitative parameter. The Coulomb's indicator is basically highly qualitative. There are ranges which gives only quality of concrete, whereas the non-steady state migration coefficient can be actually useful to give you a quantitative parameter, or at least semi-quantitative parameter, that you can use in some service life models. So that is another thing. And some measure of chloride threshold would also help to have some idea as to how to design such low clinker systems for a service life of, let's say, 75 years or 100 years. And finally, sulfate attack. Again, mortar bar expansion test in sulfate solution. As I said, it takes 6 months to do, but very often to classify new materials, it's a good test to have just as a backup. But as far as the durability indicators are concerned, moisture penetrability is perhaps significant enough or sufficient enough as far as sulfate is concerned. Because again, if you look at all of our standards, they talk about 0.45 as being a critical water cement ratio when you design concrete against sulfate attack. And that 0.45 has been born out of several tests, some lasting as much as 40 to 50 years, done by the Portland Cement Association. And that clearly shows that the role of this water to cement ratio, or in other words, porosity and permeability, is much greater than the effect of the C3A in your system, which we often talk about as being the primary agent responsible for sulfate attack. But moisture penetrability definitely is one thing which is going without any question. And when you have acidic conditions created like by magnesium-based attack, an additional protective measure will definitely help. Some other considerations, of course, when you talk about low clinker systems, you have to allow in projects for longer curing times, right? 28-day values are simply not possible with many of these low clinker systems. You can't design a 40 to 50% replacement by fly ash system to achieve the design strength at 28 days. Please be patient, wait for 56 days, if possible even 90 days. The benefits that you reap will be much more than the speed at which you can get the strength. You obviously need a clear definition of exposure, environment, and assessment of relevant transport mechanisms I already talked about. You need robust quality control procedures with laboratory and field tests. Many of these durability tests are extremely prone to error. A lot of variability happens in these tests. We found that in some tests, the variability is as high as 50 to 80%. So you can imagine different labs testing these. You need to take into account that kind of variability. And most important, of course, avoidance of cracking. Without that, you have a problem, because low clinker concretes will obviously not set as fast as OPC concrete. So early age cracking is a realistic possibility with low clinker systems. You need to design your concretes to protect them from early age cracking, especially plastic shrinkage. So that is something you need to always worry about. Thermal cracking, obviously low clinker concretes will be much better than OPC systems. So whenever you have need for mass concrete, you have to look at low clinker systems to design. So just to go forward, again, can we look at incorporation of sustainability assessment in material selection? Because very often, these technical details really don't convince people to utilize more and more of low carbon systems. But now, having matured enough, can we start looking at sustainability assessment as one of the important parameters for material selection? And this is something which our group also talked about in terms of carbon footprint reduction with respect to the service life. So we defined in the work that we had done with LC3 and other types of binders, we defined terms called apathy indices, which basically measure the total CO2 over the service life of your system, and also the energy intensity factor. That means the total energy that you provide to the system to get 1 megapascal of compressive strength. Now, combining these two approaches seems to give a much more rational method for us to actually decide what would be the right material choice for a given situation. We can't just say, okay, now my problem is carbonation, I can't use low clinker binder. No. Can I look at this kind of an approach and see what it takes or what it means for the service life, and then calculate a sustainability impact and use that as one parameter to measure? So that's something which I would like to conclude with that, and thank you all for your patient listening. All the work that I'm talking about is part of our Center for Technologies for Low Carbon and Lean Construction. Many of our students are also here. There are 15 of us faculty members in this group. I take this opportunity to also invite you to the 5th TLC2 week that is going to be held at the end of January next year. And we have an impressive line of speakers, some of whom are already here, But of course, you'll get to meet many of them in person and have a much longer interaction with many of them. So thank you all very much once again.
Thank you, sir. Thank you so much. Yeah, it's like the whole durability chapter you covered in half an hour, sir. Thank you so much for the excellent presentation. If we can take just a couple of questions. Any questions you have?
What will be the effect of using SEM on salt weathering, because it is surface phenomena?
That's a good question. We are actually finding out some interesting results there. Salt weathering wise, the surface scaling is something that we need to look at very carefully. In certain environments that we have seen with very high brine concentrations, some structures very close to seawater, where we have actually done some demonstration specimens, we are seeing the effects quite significant in terms of salt scaling, especially in a high brine, very high levels of chloride and sulfate together. So that is something which we need to look at, because very fine pore structure does not sometimes allow sufficient volume for salt crystallization, and that sometimes can lead to surface scaling. Yeah. High alumina cement. Okay, now that will be a completely different system. No, high alumina cement I'm not very aware of too much about. Of course, we've looked at high alumina cement for other applications, but I don't know if, yeah, that's going to be highly resistive to chemical attack, for sure, acids and sulfates and so on. But again, there's some problem with the long-term stability in an outdoor environment, right? Because these cements tend to lose their, their hydration products get altered with time. That makes them more susceptible to damage.
So we have one more.
Yeah. Good afternoon, sir. There's a question that you specifically spoke about longer curing times. But there is a specific challenge, especially when it comes to structures, about curing.
Yeah.
So how does how do we actually take that into account when actually using these low carbon mixes into structures?
Yeah. So definitely there's an ideal approach and a practical approach. As a professor, I'm going to only talk about ideal approaches, that you need to prolong curing times. But yeah, on site you need to take a look at what would be a doable solution with respect to the project progress and what materials are available on site. These days, of course, a lot of good curing compounds are also available. I would certainly suggest that you start looking at curing compounds. Very often, water curing becomes quite difficult for prolonged periods. Again, I think this requires some understanding of the kind of compounds available and which are most efficient in terms of reflecting to a large extent long-term water curing. But yes, you're right. There has to be some practical understanding of what is happening on site also.
Yeah, we'll close it. Thank you, sir. Thank you so much. Yeah. So that's ends the keynote, and we'll move to our regular presentations. We have the very first presentation from Chaunsali, and Chaunsali is working on the topic is on the mechanical performance, hydration and chemical shrinkage evaluation in low CO2 calcium sulfur aluminate belite cement produced using red mud and low grade limestone. Yeah.
How much time I have? 10 minutes?
Yes. Can you cut short by 10 minutes? Huh?
Good afternoon, everyone. Thanks for attending this talk. Basically, this is the work done by my former PhD student, Bipina, who recently completed her PhD thesis on this topic. So I'll be giving a glimpse of the major findings. So this is one of the special cements. I'm going to talk about calcium sulfur aluminate cement, and we'll show you how do we use the industrial waste to manufacture this cement, and we'll look at its properties, because this cement differs from Portland cement in terms of chemistry and the properties. So a little bit about the background of the cement. In 1960s, Alexander Klein in UC Berkeley patented this phase calcium sulfur aluminate, and which was used as an admixture to Portland cement to develop shrinkage compensating concrete. Idea was to get concrete which can resist the cracking due to drying shrinkage. And then in 70s, we are into BYF, belite, yelemite, ferrite type of cement, calcium sulfur aluminate belite as a sole binder rather than being an admixture to OPC. Why it was interesting? Because it showed some very interesting properties such as rapid hardening, early high strength. So these are some of the applications for repair purposes. And recently, we also see that there has been push towards reducing the carbon footprint of concrete. So the manufacturing of CSAB cement can reduce your carbon footprint by 25 to 30% because of the requirement of less limestone to make it, and also the kind of clinker you have is more porous. And one more thing, to make this cement, you don't have to go up to 1450 degrees Celsius. Instead, you can go up to 1250 degrees Celsius because that's the main phase. So how does this cement differ from Portland cement? Just to summarize, it doesn't have C3S, C3A, C4A3S, which is yelemite or calcium sulfur aluminate phase is the main phase in the cement. Apart from that, you may have belite, ferrite, and depending on the properties we want, you can dose it with different gypsum content, and that drastically changes the properties of the cement. Basically, it can make it rapid hardening system, non-expensive system, and it can also make it expensive system where there is a volume increase, again, for the purpose of developing shrinkage compensating concrete. So again, the chemistry, because a lot of crystalline phases which are present in this hydrated CSAB cement compared to hydrated Portland cement. Left you see hydrated Portland cement versus on the right micrograph shows hydrated CSAB cement. So what are the barriers? Not many. I mean, US makes it, China makes it. Why not in India? Only very few countries you see the manufacturing of such cement. So what are the major barriers? So basically, there is a heavy reliance on bauxite as a raw feed to make this cement, obviously, because it needs more alumina than what you need for Portland cement. And we also have a lack of understanding of composition property relationship. It's not very straightforward. Small differences can make huge impact in terms of properties. So we need to better understand from manufacturing perspective, and lack of standards. For an example, in India, we do not have any standard which allows the use of this cement. So, long-term durability with respect to carbonation-induced corrosion is also one active topic. How to improve the reactivity of belite in such systems, because these systems may have more belite than what you have in Portland cement. So these are some of the possible areas we all need to work together so that we can move forward in this direction. So in this presentation, I'm going to talk about two materials, two raw industrial waste. One is low-grade limestone. The limestone which doesn't meet the requirement to make Portland cement. Basically, we are talking about limestone which has less than 40% calcium oxide. Right? We have enough of this. How do we make use of this limestone, low-grade limestone, to make CSAB cement, which inherently needs less limestone, right, compared to Portland cement? That's something I'm going to talk about. And also, red mud. We have a lot of aluminum manufacturing happening in India. We have a lot of plants. And thanks to Dr. Dinakar, we could get some red mud he supplied. And we looked at this because 1 ton of alumina gives rise to roughly 1.5 tons of red mud. And you see that disposal of red mud is challenging, because of its alkaline nature, and if there are spills, it can pose environmental hazards. So we wanted to see if red mud could be a potential alternative for bauxite. So these were the two goals. And also we wanted to come up with a mixed proportioning strategy, because eventually we need to come up with a strategy which people can use. So what are those important factors which we can think of when we manufacture such cement? So I'll just show you, it's a regular process. You can proportion these materials. You have to heat it up to really high temperature. I mean, not as high as what you use to make Portland cement, but 1250 degrees Celsius. That's what I'm talking about. Then you have to cool it. You make the clinker. You grind the clinker with gypsum, and you make this cement. That's the process. I can go in detail if you have questions. And what we did in this work was we replaced the cement grade limestone. cement grade limestone, which has more than 40% calcium oxide, with low grade limestone. We looked at two types of limestone. One limestone had, more impurities, more like aluminosilicates type of clay impurities, right? And one had more siliceous impurities. That's how these two low-grade limestones differed. We were interested in seeing, like, to what extent can we replace cement-grade limestone using these low-grade limestones. So what you see, our goal was to first make sure that we are getting CSAB cement. So what is X-ray diffraction is a tool which can help you detect the crystalline phases. So clearly we see a yeelimite phase, Y. You look at the label Y is yeelimite, so we were able to form that yeelimite phase. That means we are successful in the synthesis. And you can see that something interesting, that if you go above 20-25% L1, you see a presence of galenite phase. We'll see the implication later. Okay, so just keep a note that, okay, something is happening to the system when you go above 20%. Till 20%, no galenite is formed, because that's what will help us come up with a design strategy or mixed proportioning strategy. And on the right, you see, we also compared the synthesized cement with commercial CSAB cement. And you can see, you just look at the color combination, looks similar. So we were able to kind of get similar composition of this synthesized cement as to commercial CSAB cement. So this shows you again low-grade limestone with clay impurities. We could not go up to 20%. We could go up to, let's say, 10%. Beyond 10%, you again see the presence of galenite, GE. You look for the GE letter. So there's something interesting happening there. And if you look at the microstructure, right, just to show you, okay, we can also, not just XRD, but we can also use other tools to identify what we are forming. So you can see bilite phase, you can see yeelimite phase. And also, when you have more than, let's say, 20 L2, bottom right, you see galenite phase. Okay, so that is something what we are observing. Okay, so at the end, we are interested in, the strength development. Okay, we have made this cement. What is the strength? So one thing, if you have attended Professor Pranoy's talk, we can track the heat of hydration of these cements. So this is again using calorimetry, isothermal calorimetry. We track the heat of hydration, and you can see that up to, again, the systems with 20% L1 and 10% L2 showed similar heat of hydration as that of CSAB, commercial CSAB cement. Only when you go above, let's say, 10%, let's say 15%, the blue curve, which is for 15% L2, where you had galenite formation, you saw the drop. So, okay, and again, there's something interesting happening, that when we form galenite, again, its hydrolicity is decreasing. So we'll come back to it later. And we compared it, we looked at the mortar strength, and you can see that very high early age strength, and the red line you see is for OPC. So you can see that it outperforms OPC in like early age strength. If you want very high early age strength, this is very, very good alternative. Okay, and we have compared the performance of this with commercial CSAB cement also. So yeah, we were able to match that. Now we came back to red mud. Okay, low grade limestone again is okay. Now what happens when we replace red mud? Replace bauxite with red mud, and we tried 15%, 20%. Again, we were able to synthesize CSAB cement. Only difference is red mud, if you go more than certain percent, it will again influence the color of your clinker, right? It becomes darker and darker as the red mud replacement goes up. And again, we were able to match the performance of commercial CSAB cement with the cement, synthesized cement, incorporating up to 15% red mud. Again, you see heat evolution and compressive strength development of mortars. So that was all good. We also looked at the chemical shrinkage. Okay, you can see all CSAB cements synthesized and commercial, compared with OPC, and they saw more, obviously, greater chemical shrinkage because of the reaction, because C4A3S phase is the main phase in these cements. So for unit mass of mineral, you have a higher chemical shrinkage associated with calcium sulfur aluminate phase compared to C3S. So that's what you see here. Okay, and this table shows you comparison of like initial setting time, final setting, basic tests we do with the cements. And you can see pretty much we could get standard like behavior or similar performance of these synthesized cements, right? If you compare these with the commercial CSAB cements. So that was good to know. Now the main point, like, okay, that's all good. Now, can we come up with a proportioning strategy? Okay, so we saw that the galenite is a phase which is we are seeing, and it is leading to reduction in the hydrolicity. Okay, so can we come up with, so we all know lime saturation factor we use in making Portland cement, and we understand that if it is below certain level or higher than certain level, you have some issues. So how to control the galenite formation? We propose this modified lime saturation factor, basically to control the formation of galenite in such system. Now the question was, can we come up with a single formula? No, it depends on the raw material. So for low-grade limestone, which did not have iron oxide, basically iron ferrite to alumina ratio less than 0.2, we can we have this formula with the modified lime saturation factor, and as long as it is above 90%, we will not have issue with the galenite formation. So you take any material, you calculate this modified lime saturation factor. If it is more than 90%, you are all set. If it drops below 90%, then you will have issue with the belite. Now the question comes when you use red mud, which inherently comes with lot of iron oxide, we need to modify this. Again, we have to keep in mind this iron may get incorporated in yeelimite, yeelimite phase. And we have, I can go in detail, we have verified it. It not just affects the morphology, crystal structure, basically it gets incorporated. For an example, if you have iron impurities, you promote the cubic polymorph. So not just orthorhombic polymorph, but also you see cubic polymorph when you have iron. So in that case, the formula gets modified slightly, and essentially again, this is a kind of modified lime saturation factor. If it can be maintained above 90%, we don't have any issue. So we said, okay, when your iron F2A ratio is greater than 0.2, then you use this formula, depending again on the raw materials. So in conclusions, yes, we can use low-grade limestones and red mud to synthesize CSAB cements, and we showed that we can get similar properties in terms of strength development, and we also developed raw mix proportioning strategies. Thanks again for your time, and I will be happy to take any question. Thank you.
Yeah. So one question.
Excuse me.
Yeah, please.
Related to the, how about the pH value?
Yes.
Because if saying your this specification, like after hydration, maybe the pH is low, then it will be lead to corrosion. So
Yeah.
I want to know the pH value.
Yeah. No, that's very, very good question. That is one of the issues when you use it as a sole binder. Okay, when you use the sole binder, we also saw that, yeah, it's lower than what you have in OPC, let's say 12.5, something like that. But when you, again, depending on the raw material, for red mud case, we saw increase in the pH. But to encounter that, we suggest that you can use use it as an admixture to OPC. So then you will not have the pH related issue. We still are looking at corrosion based carbonation or base corrosion issues in these systems, but one simple solution, what you are asking is to admix with the OPC so that we don't lower the pH that much.
But one case is the second time, like looking after the durability point, and again the compressive strength will be less compared to OPC in this case.
No.
Because
So
the water cement ratio looks little bit on the higher note.
You need higher there is a more water demand for this just because the chemistry is different. And you have very high you have higher strength than OPC first of all. In first 24 hours, 12 hours, and even 28 days strength, it doesn't end up, it will be similar, I would say, if not significantly larger. And main advantage is you get very high earliest strength.
Okay, thank you.
There has been enough work done in this area. I'll be happy to discuss more. Yeah.
Thank you.
Thank you.
Dr. Chonsali, so covered within 10 minutes. Thank you so much. So we have the next speaker, utilization of discarded concrete from mega construction projects as recycled aggregates by Raghupati, Kiran, and Suganya. So you just take 7 to 8 minutes. Huh? Yeah.
So this is a field level paper where we have practically executed recycled concrete at site. This is an example for other projects to follow the same thing. Okay, so construction waste is an emerging as a serious environmental and disposal issues. So energy required for crushing the natural aggregates, it's required 21,000 kilojoules per ton. Whereas recycle aggregate requires around 16,000 ton. We can save around 30.5% of energy. And recycle concrete aggregate minimize the greenhouse emission by 65%. So, okay. What is the methodology followed for this executing the recycled concrete at project level? So, for this recycle aggregate, we selected the parent concrete debris. These debris were generated from batching plant operation and sampling and testing, normal concrete pumping operations and other rejected concretes were dumped in one separate storage area. Those aggregates were braked and put in a three-stage crusher. Same aggregate were used in concrete, and these concrete were consumed in running projects, construction projects. So what are the tests were conducted? Those are the detailed. I'll explain in subsequent slides. So source of discarded concrete is we have collected the discarded concrete from batching plant spillage during the concrete production, and the excess concrete whichever generating from sampling and sedimentation tank and concrete placement operation. During the concrete pumping and after concrete pumping operations, there is some concrete debris were generating that is collected at one place and stored in one dedicated place. Then during the mass concrete production, this is the example from nuclear power plant where we are doing the mass concrete of 29 numbers of mass concrete was done, which is having a quantity of more than 2000 m3. There concrete waste was generated, then it is transported to one storage area. From there we are broken and we took to a three-stage crushing plant. From there we are produced the recycled aggregate, then we have produced the recycled concrete. So this is an example where major projects which is having this is a rough calculation we have made based on our experience and inputs from the other projects. This is the scope of concrete where major projects is having 9 lakh cubic meter of concrete, which is generating from 4 batching plants. So testing frequency, see the project specification of each projects and total provision. If you see the nuclear power plant specification, for every third miller, we have to test the concrete. After testing the concrete, where we'll dump? Then this much of transit mixture was transported for this many cubic meter of concrete. So these concrete were tested in one is production point and placement point. Then we have collected those concrete debris, and as I told, we have collected at one storage area. Then we have broken. So this is the approximate discarded quantity for executing 9 lakh cubic meter of concrete is 7,000 cubic meter. It is hardly 15,000 tons of aggregates. So this is the example. This is our projects which is in Kodangulam. So we have collected the debris. We have broken into size of 500 to 600 mm boulders. Then we have ran through a crusher. Sorry. So 20 mm aggregate and 10 mm aggregate and crushed sand. So this is the flow chart what we have followed for the recycle aggregate production. So this aggregate is not done any treatment, no treatment. So even if you are many research are there for chemical treatment, it is not going to execute at field level. So we can think of any mechanical abrasion, mechanical modification at crusher point, but field level for doing a large quantity of concrete, this is not feasible. So for this, we have not done any blending. So if you see the IS-38 provision also, there is IS-3 allows the 25% of recycle aggregate replacement. If you follow that that proportion, we can't produce that proportion in batching plant because we have to provide 8 number of bins in batching plant. That is practically impossible. So this is the aggregate where we have exposed to a environment. This by exposing these aggregates, we can absorb the carbon dioxide into the recycled aggregate. So this is the comparison what we made to the virgin aggregate to the recycled aggregate. So we can see in recycled aggregate there is only 2 governing factor. One is specific gravity, other one is water absorption. This comparison we made, and if you see the recycled coarse aggregate abrasion value is higher because of this adhered mortars. This is the chemical properties we have tested for coarse aggregate with respect to our project specification and IS 383 provision. And we have done extensive trial mix on recycled concrete for M20 and M30 grade. We have poured around 3,500 cubic meter of concrete at field for temporary structures and batching plant construction and filling, wherever the sand filling is there. We have put one CLSM, control low strength concrete for filling the sand filling. So this is the, see if you see the PCC grade we have done for maximum size of aggregate is 40 mm. So each boulders waste we want to use the even 40 mm in the PCC. For making the RCC we have used an M30 grade for constructing all our temporary structures. Even we have used in actual structure. You can see next photograph also. This is the fresh and hardened concrete studied for M20 grade. Initial slump and even for making this concrete we went for PC based admixtures which is having a advanced polymer. Because we had issues during the, this is the approval what we got from our customer, NPCL. So challenges during the mix season was rapid slump loss and even after placement of concrete there was a rapid, because of the higher side, this one water absorption, there's a rapid moisture loss. Then before the concreting, we used to do the pre-wetting, and durability indicator means we are not unable to achieve the RCBT and CMCT values, chloride migration values. This is what the actual practically place this concrete through boom blazer. And even our customer had a doubt on bonding properties of the concrete because we are using concrete recycle aggregate with the cement, whether these aggregates were going to bond or not. So we have done some pull-out test on the horizontal surface of the concrete and vertical surface of the concrete, and we have done bond test for the reinforcement and concrete bonding. So we are placed in infra works, means temporary structures and reactor auxiliary building where filling concrete was there, were unable to do the backfilling area where concrete is unable to play, backfilling is not possible. There we have done this concreting. And as I said, CLSM concrete also, control low strength material, where this fill kit is used for re-excavatable material. So this is an example where we can adopt in other projects also, where concrete waste can be used for the other purpose. The further studies, we sent these samples to NIT Calicut, where we are doing some work is going on our recycled aggregates for treatment of these recycled aggregate to use in RCC concrete. Thank you.
Thank you so much. So one question. Okay, you don't have any questions. Okay, sir.
So thank you for doing this. I think a lot of companies should adopt these things because there's a lot of wastage of concrete on site, and if you're able to set up your own crushers to reuse, nothing like it. That's excellent. Just the quantity of the discarded material that you showed, that was only the part that was taken for testing. But there's a lot more wastage also on site, no?
Yes, sir.
What do you not use that also?
Yeah,
because the quantities seem to be quite small as compared to
15,000 tons, sir.
15,000
tons.
Okay.
This is only for, not saying for STS package.
Okay, sure.
Main plant.
Okay. So I'm sure that there's a lot more potential.
Yes, yes.
So thank you.
Yes,
Very well
yes.
done.
So in your mixed design, you have replaced completely with the regular conventional
sir.
virgin aggregates with the recycle?
Yes.
100%
100%.
replacement. Okay, very good. Thank you. So we have next presentation from You have a question? Yeah, one question is, yeah.
Hello, sir.
Yeah.
Regarding this recycled aggregate, you are replacing with 100% replacement means it will not be suitable structurally. As of my knowledge, I have gone through the literatures on this study. So purely you are replacing that to untreated aggregates. We cannot get the proper strength as of mine.
That is what I
So
was
if I'm
mentioning.
not
We are
wrong.
used in temporary structures.
Yes.
That's batch implant foundations and silos and labor sets and admixture sets. Only in reactor, wherever the backfilling is not possible, in an infeasible area, that where we are done with this concrete.
And as you
It is
mentioned
not
that
used in structural concrete.
That ITZ, because of that,
Right.
majorly the strength is having an impact of.
No strength we
So
are getting.
what
Only
you
durable indicators we are
suggest-
unable to meet that requirement.
What you suggest to enhance?
SEPSI, it's a modification we have to carry in this one, crusher plant.
So you have
Well-
to replace your binders with GGBS or fly ash. That was
SEMs
slightly
and,
refined, yes. So
treated
mandatory, whenever you're using recycled aggregates, SEMs are mandatory.
Can we go
No.
for high strength concretes with
No,
the
we
recycled?
can go. The only thing is what some modification we have to do in crusher plant. That is what.
Thanks.
Okay, thank you.
Well, in your mixed design, you have used a very low water content.
Yes,
One
sir.
side you said it's having huge water demand,
Yeah.
but you used only 132 and 140 liters.
146,
Yeah, something like
Yeah,
this.
that's
And higher dosage of admixture. Did you find any adverse effects, even though it is in a temporary structures?
No,
The
sir.
dosage of admixture is much, much high, what you use.
So this
So did you
problem-
find any setting issues or something like this?
No, sir.
You
Actually,
did not
we
find.
even this concrete placed 1.5 years back. There is no even you cannot find any cracks, anything.
But did you find it's more economical?
Yeah, sir.
Because your
Well-
dosage of admixture has gone up much high.
No, sir. It's economical.
Okay.
Rate-wise. I can share you those.
It's okay.
details.
Yeah, thank you. So next we have the presentation optimizing geopolymer motor characteristics for fly ash based sintered lightweight aggregate concretes by Kanango Pratik. Kanango, you take 6 to 7 minutes. Finish.
Good afternoon, everyone. My name is Pratik Kanungo. I'm a research scholar at IIT Bhubaneswar under the supervision of Dr. Dinakar Pasla and Dr. Anushka Chandrapa. So starting with the introduction, we all know what geopolymers are, but if somebody doesn't know, I'll just explain it in a few lines. Basically, geopolymers are inorganic polymer materials or composites that are synthesized from aluminosilicate materials, which are activated using alkali activators. That produces amorphous to 3D crystalline structures. Now these 3D crystalline structures are made up of silica, aluminum and oxygen molecules, which are bonded covalently. You can see the structures right there. Now basically how it is different from the ordinary Portland cements are, traditional ordinary Portland cement are very highly energy intensive as well as produces lots of carbon dioxide. Now, geopolymer composites reduces that carbon emission by 80 to 90%. Now, going on with the objectives, I started with the analysis of the properties of geopolymer motor and correlated them with the parameters that affect those properties. In addition to that, I also tried to correlate and the impact of those parameters at the microstructural level as well. Now, the scope of these objectives would be to formulate a strategic technique that can help us to get an optimum mix designation using fly ash and ground granulated blast furnace slag as binders, which will be further utilized in sintered lightweight aggregate based concrete. In addition to that, we'll be also analyzing the factors that influence these physical, mechanical and microstructural properties and define those characteristic properties for the motor specimens as well. Also, we can use this to understand the correlation between the physical and microstructural properties, thus concluding the optimum mix design that we require for the concrete. Now, for the materials that I have used, we have basically taken fly ash and GGBS. In comparison to OPC, we can see the specific gravity to lie on a lower side in comparison to the OPC, also the bulk density as well. Now, for the chemical properties of the alkaline activators, we can see that the sodium silicate has a silica dioxide content of 29.5%, whereas sodium hydroxide has a sodium oxide content of 45.8%, which is basically a useful composition required for the geopolymerization process. Also, for the XRF analysis of the binders, we can clearly see that the major content in OPC is calcium oxide with 62.5%. But in case of fly ash, it's silica dioxide with 59%. And in case of GGBS, all of the calcium oxide, silica dioxide, and aluminum oxides are present, which are basically good materials that require for the geopolymerization process that produces the NaSH and CSH gels. Now, for my methodology, I have taken two parameters, the constant parameters and the variable parameters. The constant parameters include fine aggregate to binder ratio as 2, the sodium silicate to sodium hydroxide ratio as 2, and the curing conditions to be an ambient curing condition. Now, for the variable parameters, I've taken the binder ratio to vary between 80:20, 70:30, and 60:40, where the binders include fly ash and GGBS by volume. And also the alkaline activator to binder ratio includes the ratio of 0.4, 0.5, and 0.6. In addition to that, the sodium hydroxide molarity includes the variation in parameters of 8, 10, and 12. Now, including all these variable parameters with the values, I created a Taguchi analysis, which in turn created a Taguchi orthogonal array, Ln orthogonal array. Now, in addition to that, I've also taken the signal to noise ratio. Now, signal to noise ratio basically of 3 types: larger is better, smaller is better, and nominal is better. For this experiment, I have taken the larger is better approach for the compressive strength and flowability as well. This is my experimental program, and this is the Taguchi Ln orthogonal array that I've adopted. Here we can see that the fly ash is to GGBS ratio with 80:20, 70:30, and 60:40. The alkaline activated to binder ratio with 0.4, 0.5, and 0.6, and the sodium hydroxide molarity variation with 8, 10, and 12 molars. Now, this is the mixed proportion that I have created with a total mass of 3 kgs, where per mix mass is varying between 0.833 and 0.882. For the experimental procedures, I have added the alumina silicate precursors with natural sand for a dry mixing, and then I have added the sodium hydroxide and sodium silicate simultaneously, mixed them for 180 seconds. Then I have created a geopolymer paste, and after that I have tested for the flowability and then casted into cubical specimens of 70 mm. Now, for the testing of the specimens, I've tested the fresh property using the flow table. Then I've casted the motor castings and conducted the non-destructive testing at 28 days using the ultrasonic pulse velocity test. After that, I've tested the mechanical property test using the compressive strength testing, and later the macrostructural property using the XRD. For the results, we can clearly see that the flowability here for the L04 mix shows the highest value, and we can clearly see that all the values, the variation between, lies between 110 mm to 160 mm. Although there are no specific regulations available, but if we compare with the cement mortar, IS 2250 of 1981 specifies the acceptable range of 100 to 150 mm. Also, for the ultrasonic pulse velocity test, we can clearly see that all the mixed designs except L01 lies within a range of 3500 to 4500, which is clearly acceptable range given by IS 13311 of part 1 of 1992 for a good graded concrete. Also, after that, the compressive strength, we can clearly say that L03 has the highest compressive strength with 53 megapascals, followed by L04 with 52 and L05 with 50.5 megapascals. Now, we can clearly see that the compressive strength value increases with the increase in the alkaline activator to binder ratio, as well as the molarity of sodium hydroxide taken. In addition to that, as the quantity of the GGBS content is increased, the compressive strength value also keeps on increasing. For the X-ray diffraction test, we can clearly see that the XRD analysis of L01 mix gives a photon scattering density value of 2550 decibels, whereas in case of L04, it gives a photon scattering density of 4100 decibels. Now, these peak intensities shows the positions of the quartz value, which is a major strength enhancing factor. Also, between these phase angles of 27 to 29 degrees, we found the amorphous NaSH phase, which is responsible for the intermolecular bond, and also shows that there is a successful geopolymerization process. We can also find CASH phase present, which are basically broad hump-like features in 28 to 31 degrees Celsius. For the result analysis, we adopted the S by N ratio. Here we can see the orange line showing the flowability curve and the blue line showing the compressive strength curve. We can clearly see that the intersection point at L04 gives us the optimum mix designation portion. We can also see that L08 gives out the intersection point, but using too much of alkaline activators, the cost benefit analysis would be on higher side. For quantifying the S by N ratio, we can clearly see that the L03 shows the maximum value of S by N ratio, but L04 shows the optimum value. Similarly, in case of flowability, we can see the maximum value in case of L07, whereas the optimum value comes out to be in the L04 mix design. For the conclusion, we can clearly say that the Taguchi orthogonal N-line array helps us to quantify the influence of binder ratio, alkaline activator ratio, alkaline activator to binder ratio, and NaOH molarity to give us a robust mix design, as well as to ease us to gives us an ease to accept an optimum mix design out of it. In addition to that, for the flowability analysis, we can clearly use this methodology along with the balanced S by N ratio to get a workable geopolymer motor. Also, for the compressive strength, we can clearly see that the increasing value of alkaline activator to binder ratio, sodium hydroxide molarity, as well as the GGBS content clearly increases the compressive strength values also as well. In addition to that, the XRD analysis also confirms that the higher the PSD value or the photon scattering density value, the denser is the microstructure, which is basically characterized by quartz or aluminosilicate gel. Thus, we can say that by combining the Taguchi and S by N results, the optimum mix design can be established using a very scientific method, which does not waste any raw materials and also reduces the time and energy consumed during the heat and trial methods typically employed. For the future work, we can go ahead with the FESEM and FTIR analysis, which will help us to understand the micro changes in the matrix of the geopolymer motor. Also, we can use this optimix for incorporating into SLW-based concrete and study its further characteristics. Thank you.
Take one question.
Okay. Why do we need a flowable motor, basically? So basically, my requirement is I need a motor that can be incorporated into aggregates also. Like for using this motor, I'll use the aggregates as well and create a concrete out of it. Now, the more flowable it is, the more easily it will be in practical application basis as well. So if I consider for practical application in wall sections or somewhere, we can use this as more flowable concrete base.
Yeah. Thank you, sir. Thank you, Pratik.
Thank you.
So we have the next one coming up by Sahu and Gupta. Long-term performance of carbon sequestrated geopolymer stabilized earth exposed to 1 year of natural exposure, microstructural and mechanical performance.
Good afternoon. So my name is Pitabas Sahu. I'm a PhD research scholar from Center for Sustainable Technology, IISc Bangalore. I'm working with Professor Saradvi Gupta. Today I am going to present on long-term performance of carbon sequestration geopolymer stabilized earth exposed to 1 year of natural exposure, studying the microstructural and mechanical evaluation. So why I am more interested to look after the excavated earth. Generally, the excavated earth contains soil, all those materials, and the laterite clay-based soil I am using here. And soils are exposed, they are susceptible to moisture. So they are so to start understand the swelling and the shrinkage effect on long-term basis. We are now I am studying the long-term performance of carbon sequestration geopolymer stabilized material. So here are the contents. I will give a brief introduction, methodology, material characterization, and microstructural mechanical performance, and followed by conclusion. So first I want to introduce, every year we need 50 billion tons of fine aggregate and this excavated soil which it constitutes 60 to 70% of construction and demolition waste in developing countries and 30 to 40% of in developed countries. And annual production of excavated soil also are in billions. In China alone, it is produced by more than 2 billion ton, and in India it is 80 to 100 million ton it is reported, which is much higher than this reported value. And how I have performed this study means initially 3.5 years back we have utilized not only this excavated soil as a fine aggregate source, we have utilized as a natural means as a clay source to improve the rheological performance of 3D printable material. So successfully with blast furnace slag and fly ash as a binder and partially replacing excavated soil with fine aggregate, we developed a printable material with binder to aggregate ratio ranging from 1:1 to 1:3. So successfully we developed very linear mix proportion, which is binder to aggregate ratio 1:3, that is 0.33, which is not done yet till now. So and with lower molarity also, with 4 molar also, we got the 3D printable material. So further, I have studied the geopolymer-based earth-based material, how the yearly age carbon sequestration impacts the long-term performance. So here at one day, I have we have sequestered carbon dioxide with a 5% concentrator for 4 hours, very short period of time. So it is followed by 28 days on 27 days of dry curing at laboratory condition, because geopolymers doesn't need extra additional water, and followed by 1 year of natural exposure condition to sun and rainwater. Why it is it is important to study, because this clay-based material are susceptible to moisture, and it can be exposed to the repeated cycle of wetting and drying and temperature variation, daily temperature variation, and even if the rainwater how it is increases and how leaching of the geopolymer-based material happens, we can study through this, and we can understand the mechanical performance. So these are the material characterization. Means this is the soil. So this is the manufactured sand, which we have replaced with partially replacing with some excavated soil. So this excavated soil, it is classified as a medium plastic clay soil, where clay content is 40 to 40%, and silt is 12%, and sand is 46%. Liquid limit are 33%, and plastic index is 16%. So it is a low medium or low plastic clay soil, and the primary mineral present is kaolinite and montmorillonite. So in the past, we already know that kaolinite is successfully utilized as a alumina silicate source in geopolymer-based material and OPC-based material. And from the morphological study, we can see that this excavated soil, these are more rounded in structure. So this is why this is performs better in 3D print to improve the 3D printability of the material, which is I'm not discussing today. The excavated soil mainly consists of alumina silicate and oxides, and the alumina silicate percentage is more than 80% combiningly. So the microstructural degradation, I will study with in three tests. So one is SCM, another one is XRD, followed by NMR. So from what we exactly get from SCM? So at one day, we can see some sort of shrinkage cracks are generated before accelerated carbonation due to incorporation of this geopolymer-based material and higher rate of hydration. However, these are filled with sodium carbonate-based material when it is accelerated carbonated. And further, when at 28 day, we can see suddenly a lot of calcite has been grown. And at 360 days, we can see the calcites are washed away, or it's not visible. And suddenly, the cast gel has been become porous, and very small amount. These are also calcite, but these are smaller in size. So how exactly we represent this microstructure analysis? At one day, the carbon dioxide get incorporated to form carbonic acid, and it is reacts with sodium hydroxide to form sodium carbonate and NaSCO3. And further, this carbonic acid and aqueous CO2 reacts with this Cassna's gel and to form calcium carbonate and alkali silica gel. At 28 day, this calcium carbonate form, they grow in their size and followed by when it is exposed to outdoor exposure condition, slowly the calcium carbonate has been leached away. This is why we are getting a lot of porous structure, and followed by sodium, leaching of sodium and aluminum. Why this calcium carbonate has been leached away? Because generally at pH 7, the calcium carbonate is solubility is only 2 to 3 gram per liter. But when the water become acidic at acid rain condition or slightly mild acidic condition, so the pH means solubility of calcium carbonate increased to 12 instead of 2 gram per liter. So further, we have studied the microstructural changes by studying the XRD. Here, I just means summarizing whole story. So in the control means when soil is not present. So the lot of pirsonite, calcite, thermonitrite are formed, and aragonite also formed. This is also very similar in geopolymer-based excavated soil. When it is incorporated, it is very similar to that. But the interesting thing is here. This is kaolinite. The kaolinite peak is lower than the carbonated one. That means when it is at 28 day, the carbon how much Cassna's gel is required to encapsulate the kaolinite may not be there. That is why the bigger kaolinite peaks are available. So the most interesting thing is here means the crystalline pressure of calcite. The crystalline pressure can be formulated as 2 gamma Cl divided by R. The main ratio means proportion we want to see this R value. This is the pore radius. So if the pore radius is 50 nanometer, the crystalline pressure can be more than 22.5 megapascal. This is the most interesting part of this story. So this crystalline pressure grows when the pore radius has been reduced. That means when this calcite and waterite, their size is generally 2 to 50 nanometer. When the size grows, when water it is absorbing by water, the crystalline pressure also increases. So that exceeds the tensile strength of the geopolymer-based material, and that creates expansion pressure. So how that expansion pressure impact? So this is further. Sir, 1 minute remaining, sir. Oh. So microstructural study, we can see that the kaolinite peaks, which are before carbonation are visible, they are become more prominent when acceleration carbonated. So similarly, this is more confirmed by aluminum NMR. So this kaolinite peak in geopolymer gas-based material is very prominent. And why this geopolymer-based material is much more? Because the calcium to silica ratio is higher in control-based material, means when no soil is there. When soil-based aluminum silicate reacting with the material, this is the kaolinite peaks are more prominent. And further, this is the schematic diagram. We can see when it is accelerated carbonated, the dense Cass gel has become porous, and sodium carbonate, calcium carbonate minerals grows on, and slowly they are leached out in the when it is exposed to 365 days of exposure condition, outdoor exposure condition, and slowly these clay minerals expands with respect to time. They expands, contracts when it is exposed to a repeated wetting and drying condition, and altogether the geopolymer material has been deteriorated. So these are the geopolymer stabilized earth. This is natural carbonate material. It is very looks sound. However, when this carbonated accelerated carbonated geopolymer mix naturally exposed to natural carbonation, the clay particles, removal of clay particles can be visible, and cracks has been appeared. But how does it impact the mechanical performance? Here we can see at one day the strength has been increased, but at the same time when it is exposed to 365 days outer condition, the strength has been deteriorated. This is attributed to more importantly the higher porosity of the material, and this is most interesting thing is the drying shrinkage here. The drying shrinkage, however, due to carbonation, it decreases, mainly attributed to the expansion pressure created by the calcium carbonate, and the larger pores are available. So this concluding my altogether work. At one day when we are carbonating, lot of sodium carbonate has been produced. So this sodium carbonate slowly get leached away, or they act as a source to further carbonation of Cash-Nash gel. So this Cash-Nash gel slowly again deteriorated due to formation of calcite, and long-term performance, how it impacts, shrinkage reduces, but strength has been decreases, and altogether the material start getting, the clay particle getting expelled out. So these are this is published last year in material sustainability, and this is collaborated with Professor Sheetal Jain from SSU at IAC Bangalore, and yeah, that's thank you very much.
Thank you so much.
So just 1 minute. Sorry, just 1 second, sir. So altogether, just to conclude the story, this geopolymer earth-based carbon sequestration, accelerated carbon sequestration material shouldn't be used at the current condition. Based upon my experience, incorporation of silica and reduction in small porosity can be more helpful to improve the refining of the pore structure, which can be in future it can be done in future.
Can I take one question? Anyone?
You're using the excavated soil which has got a lot of clay content.
Yes, sir.
And it swells a lot.
Yes, sir.
Thereby the shrinkage cracks and other things develop a lot. Even though you are showing very high strength on one side, but with over a period when it expands and cracks, and the strength also gets reduced.
Yes, sir.
So what is this reduction of strength that is coming up when the cracks have come, and where do you propose to use this material?
This is it can be utilized a low, non-structural element, different non-structural element it can be used.
Like bricks and other things you want to propose?
It can be used, and its strength reduces, but still the strength is more than 30 megapascal, means 25 to 30 megapascal. So it is can be utilized in different aspects. And why this is swelling and shrinkage cracks are generated? Because of the properties of clay particle. And the clay particle, they have a plasticity index of 15 to 16. So when the water has been absorbed, they expand within the material. So they also create or exert on pressure within the material. So that is why if the strength of the material will be lower than the exerted pressure, then definitely there will be cracks and all the things will happen. Otherwise, it can be utilized as a to improve the lowering the total porosity also. Means it will create an expansion pressure, or altogether the strength can be increased also.
All right.
So this is why if we can incorporate in future some pore refining material, the water molecule may not reach there, or if the strength of the material can be increased, definitely also it can be.
Yeah, it is important to plug the pores, because as clay expands and cracks, more and more water will be coming, and it keeps on swelling and increasing.
Yes, sir.
So you have to add something more to reduce that.
It's a preliminary study.
Wonderful.
So we have developed the mechanism.
Good study.
Thank you, sir.
Thank you. So we have next one. Thank you, Mr. Sahu. We have next one coming from Mangalapuri V and Valluru U. Yeah. The topic is a study on physical strength and fracture characteristics of hybrid fiber reinforced fly ash and slag-based geopolymer mortars activated using water glass. Only 8 minutes, huh? Oh, yeah, try to wind up.
Sir, shall I start? Good evening to all. My name is Venkateshwarlu. I am assistant professor from Vardhaman College of Engineering, Hyderabad.
Today I am here to present my topic is on study on physical strength and fracture characteristics of hybrid fiber, reinforced fly ash and GGBS geopolymer mortar using only water glass, that is neutral grade. So instead of sodium hydroxide and sodium silicate, in my study we are using only neutral grade sodium silicate or water glass. So my other members are V. Usha Rani, research scholar from NIT Warangal. Gudem Shivani, she is a PG student from my college. She is my student. So coming to the contents, this is the introduction. First one is introduction, motive of the study, and scope and objectives. That means methodology, results and discussion, and conclusion, selected references. So as you know that, we are all know that concrete is the largest consumed material in the world. So since which is having some of the benefits, it is cost effective and recyclable, low maintenance and easy to work with, water resistant and durable. We are all know that apart from these advantages, some drawbacks are also there, which can produce CO2 emissions and energy intensive, and which can cause global warming. So it can produce or generate dust also. So it can create some natural depletion of natural resources. So for 1 ton of producing OPC, we need 2.4 tons of raw materials. So around the 7% of CO2 emission by the concrete. So 50% is from the chemical process and 40% from the burning of the fuels. So which can cause depletion of the natural resources as well as which can create the greenhouse effect. So we can reduce these type of effects. Major concern about CO2 emissions. We need a new sustainable construction material that may be the geopolymer binders or geopolymer composites or alkali activated emerge as a possible solution, one of the possible solution. So this is the motive. For this study, I have two motives. One is even though the geopolymer concrete or geopolymer composites having maybe reduced carbon footprint, but to producing this geopolymer mortar, we need an alkaline solution. That alkaline solution is consisting of sodium hydroxide solution as well as sodium silicate solution. So we want to produce that. That means the cost of the alkali activated binders or geopolymer binders or composites over 40% is influenced by the this alkali activator only. So so my motive is instead of using two types of alkali activators, so that is one is increasing the CO2 and the second one is the cost when we are going for the higher molarities. Of course, in lower molarities, such type of problem is very less. And when we are using the higher molarities of NaOH solution, there may be a problem of that means risk also because of this concentration of the NaOH. We all know that. So we instead of using two solutions, that is one is sodium hydroxide and second one is the sodium silicate. Instead of these two solutions, we need to use only one solution, that is the neutral grade of sodium silicate. That is one idea. So coming to the second one is, so as we all know that the geopolymer composites or geopolymer binders having the superior strength and durability properties. Apart from this, there may be some limitations in the using the geopolymers and alkali activated composites, such as cracking behavior and ductility, since when we are going or we are using high molarity of alkali solutions as well as the high amount of the GGBS content, there may be some higher brittleness will be there. So this is one of the drawback, one of the limitation of the geopolymer concrete, not only in geopolymer concrete, in conventional also. So to overcome these problems, we are adding some fibers in the form of short and long in discrete form. So then such type of fibers will, that means will help when the multi-directional load is acting on the particular member. There may be some helped by these fibers. One is they are arresting the crack, and one more thing is they are resisting the crack propagation during the loading. So those are the major advantages of when we are incorporating the fibers. So Of course, we are adding the one type of or one size of fibers in any, that means in a mix. So the one type of fiber or one length of the fiber will maybe help some type of benefits only. For example, if you are taking the short-term fibers, they are helpful in the pre-crack behavior. When we are considering the long fibers, they are resisting the crack propagation, which means they are very excellent in the post-crack behavior. So therefore, why we need to go for fiberization or grading of fibers, just like that means graded aggregates. So, and one more thing is, nowadays the trend is we are using the ternary blended binders or ternary blended materials in the geopolymer concretes. So why we are not going for blending of fibers? That means different sizes of the fibers in different types. So that is also one of the motive. Through these motives, I have to frame two objectives. One is pressure and strength properties of a geopolymer mortar using different types of monofibers and hybrid fibers. So, and second one is that to quantifying the improvements because of this incorporation of the mono and hybrid fibers. And in addition to this, we are also studied the fracture behavior because of this. Okay, sir. Okay, sir. So this is my methodology. So for this, we have to using three types of fibers: 30 mm steel fibers, 12 mm basalt, and 6 mm different grades or different lengths of the fibers for the fiber gradation or blending of the fibers. Those are the percentages. These are the hybrid combination. So these are the fibers we are used. These are the specimens we are casted. This is the physical test we are carried, and that is the compressive strength tested. So that is the actually properties of the fibers. That means different aspect ratios for the steel fibers 60, basalt fiber 300, glass fibers 150 only. So these are the mixed proportion for the three combinations we are used. In the combination one we are used, that is control one. In combination one we are used, one is, so one more combination in this that is not visible here. So one is 0.75 steel and 0.25 basalt and 0.75 steel and 0.25 glass. And third combination is the total volume of the fraction is the one only. We are setting that one. So third one is the 0.7 steel fibers, 0.15 steel glass and basalt fibers. These are the test results. So in my initial study, we have studied different combinations of the fly ash and GG-base proportions. BG-base and fly ash proportions. As we all know that the standard consistency value increased as the GG-base content is increased. When we are using the water glass only. Water glass also, not only in the sodium silicate and sodium hydroxide solution. In this also, the same situation, the same scenario we are observed. So in the initial setting time and final setting time also same. So these are the values. So these are the compressive strength values because of these steel fibers and basalt fibers and glass fibers, and the last one is the hybrid fibers. So these are the improvements because of the steel fibers, around 10 to 13.3% improved. Similar observations, similar results also observed in the previous studies such as Nematolus and Al-Mazid, 10 to 15%. In glass fibers, basalt fibers also around 7.5 to 8. In glass fibers 6 to only 6.5 only, very less compared to the basalt fiber. Since compared to this, the basalt fiber having the better tensile strength and better value. So coming to the hybrid fiberization, 14.5 to 15% of. So this is the fracture behavior. So these are the peak load, and this is the fracture energy. So these are the final conclusions. So around the standard consistency and compressive strength, around 15% was observed in the hybrid combination. This is the highest, 15.3. Coming to the peak load, 23.3% at the hybrid combination. That is 0.75% of steel fibers and 0.25% of the basalt fiber. Similarly, in fracture energy and peak load also same. So finally, what I can say is these results underscores that the benefits of the optimization of different GG-base and fly ash proportions and usage of neutral grade water glass will be that means will be the effective solution or will give the significant results in the form of strength and fracture response in geopolymer systems. That's it.
Thank you so much. It's wonderful work. Yes.
So
any questions? Yeah, we can have. Okay. Thank you so much. Yes. Okay, they have the next one coming up. Influence of carbon curing on the performance of biochar geopolymer concrete by Valluru and Naika. Here, Valluru. Yeah.
Good evening, everyone. This is Usha Rani, and my study title is Influence of Carbon Curing on the Performance of Biochar-Based Geopolymer Concrete under the guidance of Professor P. Ratish Kumar, sir, from National Institute of Technology, Warangal, and along with him, R. Ramesh Naika, professor at IIT Dharwad. And this is my contents. And coming to the basic introduction, we all know that because of the cement industry, we are having 7 to 8% of CO2 emissions. And in the direction for achieving the sustainability in the construction field, we need to find the alternative material material for the cement. So one of such alternative is utilization of alkali activated binders. So alkali activated binders are produced through the activation of clinker-free supplementary cementitious material with the alkaline solutions, and it will produce as the geopolymers. And the basic advantages of geopolymers comes under they having very low carbon emissions and high mechanical and durability performance, especially high fire resistance and better low embedded energy. And the main motto is to basically India is a developing country. It produces around 500 million tons of agro waste. So this not only agro waste, it can produce agricultural waste and non-agricultural waste. So with the open burning of these agro and non-agricultural waste can lead to the air pollutions. Recently we had know that Delhi faces too much air pollution because of this open burning of agricultural waste. To reduce such type of hazardous, we can utilize that agricultural waste and non-agricultural waste and converted them into biochar in the absence of oxygen. With the thermochemical treatment, we can produce biochar. So this biochar will act as one of the alternative for the open burning of bio wastage. So here this picture will address the overall circular economy of utilization of biochar in the construction industry. Here, with the production of 1 kg of biochar, we can produce, it can absorb the around the 3.3 kgs of CO2 equivalent of biochar. So the main motto of the study is, so for in the direction of developing green concrete, so I have used the biochar with the geopolymer combination and developing a green concrete, and to access not only our material to become a low carbon, to making it as a long-term carbon sink, I am using accelerated carbon curing method to capture the carbon dioxide. This is the main motivation, and the main objective is to I am going to develop the geopolymer concrete with a partial replacement of biochar as binder replacement, and I have to study the what is the variation of mechanical and durability performance with respect to the curing conditions. And the research methodology I have followed here is, first I have synthesized the biochar and then basic characterization. So once it is fulfilled, then I have to develop the biochar-based geopolymer concrete. And here I have followed the two different curing methods. One is ambient curing and another one is carbon curing. So after completion of carbon curing, I have done the mechanical performance and the durability assessment. Here in the durability assessment also, I have followed the novel technique, that is deterioration of acid deterioration using the image-based analysis. Here I have used the hue saturation intensity analysis for acid deterioration. And this indicates the basic synthesis of the biochar. Here we have collected the raw biomasses, and we have sent it to that raw biomass into pyrolysis using tubular furnace around 400 to 500 degrees Celsius. After that, we have got the granular biochar. So from that, we have done some mechanical ball milling for getting the required size. Here I have used it as a replacement of binder. So that's why we have collected the biochar in such a way that it should pass from 90 microns. And coming to the basic characterization, I have done with the particle size distribution. And the basic size of the particles lies around 10 to 20 microns of my wood biochar. And the morphology is most of the particles are like, they are in flocculated nature, and they're having a tubular vascularity exists because of the pyrolysis at 400 to 500 degrees Celsius. And then the chemical composition, it includes, most of the, it's having amount of silicates and aluminates. So this will further say that we can utilize this as a supplementary, not supplementary, as a replacement for supplementary cementitious material in geopolymer. And this is the mixed design details. And I have used the 50 to 50% of fly ash and GGBS in my mix. And I have followed the 12 molarity with 0.55 solution to binder ratio. And here the protocol for the carbon curing I have followed is, after 24 hours of demolding, I have placed the specimens into accelerated carbon curing chamber for 3 days with a CO2 percentage of 8% and with relative humidity of 60 plus or minus 5 degrees centigrade at a temperature of 24 degrees. And I have done with the paste characterization. So from this paste characterization, I have let you know, we could understand that with the increasing, I have utilized 3 different combinations of with different dosages of biochar. One, I have started that 0% WB indicates the control mix, and with 1 to 3% of WB. So with the increasing of WB from 1 to 3%, we have it requires the more solutions, and similarly the setting time will getting decreasing order. And the second one is we have done with mechanical performance. Here I have compared the 7 days and 28 days compressive strength along with the 2 different curing conditions. So from the 7 days compressive strength results, we got to know that there will be an increasing of compressive strength with the increasing of biochar dosage from 2 to 3%. And this improvement was observed around 14 to 15% of improvements we have observed. And whereas in the carbon curing, that improvement was increased little higher. For example, for 3% of wood biochar, we have achieved around 25.80% of compressive strength when compared to the control mix. And after the mechanical performance, we have conducted the acid durability. So we have exposed the specimens for 5% H2SO4 and HCl acids for 28 days. So this picture will indicate how the deterioration will happen after 28 days of deterioration. And here the first one is that is with the control one, and the bottom will indicate with the 3% of wood biochar. And we have we have done the mass depletion factor, like mass loss after 28 days of curing. Like this mass loss was showing, like the reduction of mass loss was observed with the increasing of biochar dosage. At the same time, if you compare the comparison, if you make the comparison between the ambient curing and carbon curing, that mass loss will become very low. Thus, these lower results will achieved because of the pore filling effect of the biochar. Similarly, we have done the strength degradation factor, strength loss also. So here the strength loss also following the similar pattern as like mass loss. And here we have introduced the novel methodology, like we have captured the images of concrete using high resolution DSLR cameras, and we have converted that RGB values into HSI color conversion. So this color conversion, we have used the ImageJ software. So we have come up with how the hue values will vary with the increasing of biochar. So basically hue represents the true color of the specimens. So because of this H value, we didn't say exactly what is the deterioration, but the next parameter is I value. I is nothing but intensity. Intensity is brightness. So because of this brightness value, with the increasing of biochar dosage, we have got the lower brightness value. This lower brightness value will achieved because of, whereas for plain geopolymer concrete, it having the higher deterioration, so more aggregate pop-outs will coming, so it will give the higher intensity value. But whereas for geopolymer, we are getting lower deterioration. So because of that, the aggregate pop-outs and that binder material spalling will become very low. So that will create the lower intensity value. So similar pattern, yes, also following. So overall.
Good. Yeah, it's a wonderful work. So any questions? Yeah.
Yeah. So, why are you doing carbon curing? What is the
Sir, the main motive is generally for cementitious material, if you go for prolonged carbon curing for capturing of too much carbon dioxide from the atmosphere, it will create a problem to the reinforced concrete if you use it in a reinforced manner. But whereas if I use the geopolymer with the combination of biochar and carbon curing, here there is no formation of Portlandite, so because of that it won't affect the pH level of my concrete, so I can use it in a reinforced manner also for capturing long-term carbon dioxide.
I wanted to ask what is there inside your geopolymer which is capturing the carbon?
Basically, that biochar is not having that much carbon capture capacity. Geopolymer not having carbon capture capacity, but the biochar having carbon capture capacity.
Biochar is already carbon negative. Once you have converted to biochar, it's carbon. Why carbon will capture carbon?
Sir, it's having a high porous nature and it's having carbon affinity to absorb it. So that's why from the literature we have find that it's having high absorption nature.
What I think we should try to avoid carbon curing for geopolymer system as such, because we saw in previous presentation, it's actually deteriorating. It will reduce your pH. It will disturb your gel formation or whatever is forming geopolymeric product. It will. So I think we should try to avoid carbon capture. Carbon curing of the geopolymer.
Sir, we'll explore it little bit. As of now, from the literature, we have find this gap.
Thank you so much. It's wonderful. So I think we are done with our presentations and sessions for this this 2:30 to 2:55 session. So that's it. And thank you so much, all of you, for coming for this session. And I'm so happy for chairing this session. And thank you, ACECON, for giving me this opportunity. And thank you so much.
Thank you very much, sir. Now it's time to felicitate the keynote speaker, Professor Manasantanam, and the session chair, Dr. Dinakarji. So I take this opportunity to felicitate the session chair and the keynote speaker. And may I now request Dr. Shishir Bansalji to join me in felicitating the dignitaries, please. Dr. Anchuri also, please. Keynote speaker I say Pune chairman, sir. Abhi.
Session chair.
I hope all of you had a great time with the session. We'll be starting the next session within next 10 minutes. All the speakers are industrial speakers. Please do have a coffee break and join back in 10 minutes. Exactly 10 minutes, we'll be starting the next session. Thank you all. Yes, sir. Yes, sir. I'll do it, sir. I'll do the film. Good evening, all. We'll start our next session with prominent leaders in civil engineering leading beautifully in our country with different respected positions. Our session chair for this session is Dr. Shishir Bansal. He holds the senior position of Additional Director General at the Central Public Works Department, a premier engineering organization of the Government of India. His professional work and research primarily focuses on civil engineering, including highway and bridge projects, sustainable development in the construction sector, assessment of environmental degradation during construction. He has also been involved in major infrastructure works such as the Signature Bridge project in New Delhi. We welcome you, sir.
Thank you, Lalita. So good evening to all of you. By the evening, generally attendance get less. But we are having 4 very, very important presentations, all invited presentations. I think whosoever is not present here will miss this presentation. The first presentation is from L&T, Advanced Concrete Technology, the game changer for speed and scale in Mumbai-Ahmedabad high-speed railway. The country is seeing the first high-speed rail construction. And though Mr. Sithali Kumar was present, but now Mr. Amit Barde. He's present here, Mr. Amit. I know he's an excellent presenter. I have listened to him earlier also in Delhi. Please, Amit, welcome.
Okay, good evening all. I think Mr. Senthil Kumar from L&T Heavy Civil was going to present. Unfortunately, he had a medical emergency at the very last minute. He's doing all right, but no travel was recommended. So one last, this is a last minute change, so I said, okay, I was presenting in another session anyway, I was here, so I said I will take it up. But having said that, high-speed railway is a different IC and a different project. So we discussed with the organizers and we said that it would not be prudent for me to present on high-speed railway. There are other obligations also. So the topic was game changer in industry and we are talking about precast. So I said, okay, I will talk about precast. You will see some high-speed, I will tell you where. But you have to bear with me saying the topic, everything is changed at the last minute. We were not prepared for this. My another presentation starts there in another 40 minutes. So I will walk you through this. But the theme of the conference, I think we'll try to maintain, right? It is still concrete, what we are doing, the advances in concrete and how we will do it. That's the agenda. I think I have about 30 minutes. So I will walk through it. The topic here is going to be that precast construction for high-rise buildings, whatever that we have been doing, L&T is doing for last 10 years, how it has evolved, why we are doing it, to a certain extent how we are doing it, and then where will we take it. Now precast construction is not new. We have been doing that for all along in infrastructure. We are doing that in large commercial projects. This is our Shri Narendra Modi Motera Stadium, total precast, one of the largest stadiums in the world for cricket. The seating capacity is about 1,25,000 seats and completely precast. Very unique, very challenging job. When I said high-speed railway, I'm going to show you, this is high-speed railway, right? So this is the girder of high-speed railway. It is 40 meter long. It's 1,000 tons, a single cast. And if you talk to that project site, they are more excited about that straddle carrier that was built in-house by L&T in India than the girder. Right? And because that girder has been a mainstream system for them, they have been doing that for 30 years. We have improved the technology where we do the long spans and all, but still that's a day-to-day business for that sector. If you look at the same thing, this is the Atal Setu project, what we did in Mumbai. It's operational now. One of the longest and second longest sea bridge in Asia. This is a hybrid technology where we are looking at concrete girders, where we are looking at long girders. Again, this picture, it's not a concrete girder, but it's a 150-meter long element, 12-meter wide. It's OSD, the orthotropic steel deck. And if you want to take a scale reference, you highlight at that red box, and those are the people standing. And now you take a look at it one more time on the barge, then the girder. Right, that the barge is also built in-house, and the barge is carrying that girder in sea winds with not more than 5 millimeter up and down and installing it on the bridge. The girder itself is, like I said, 150-meter long, and it's getting installed on that piers in just about 2 to 3 hours. What used to take months, we are doing that. And we are doing that because the projects in India scale is now demanding it, right? It is not like something we want to do something fancy and show it how fast we can do. All those efforts to build that deck outside on the coastlines, put the barge, bring it and install it, because the project scale is going and it's demanding. And if I have to summarize all those projects, when we start looking at our own business strategy or our own business models, I think you come back to this one screen. If you long to look at that business excellence in India, the mantra that we feel through the last decade that is emerging is mechanization and digitalization, right? And these have become the buzzwords now. Everybody is talking about it. But the people who are doing behind it, if you put the contractor's hat, if you want to complete that cycle of that business excellence, what we feel is that mechanization is leading to that efficiency. That efficiency is being tapped by your digital efforts, what we do, and we're going to talk about that some. And then that efforts is leading to innovation, and that innovation is leading what more mechanization we have to do, right? And the crux behind it, the way we look at it, is the continuous marginal improvement. In our industry, it's very, the inertia is pretty heavy, so nothing changes overnight. It takes long time to get things also. What we have followed is that mantra again is the marginal improvement. Keep tweaking things, keep doing small things, but lead to changes. So with that background now, if you will see where precast construction has evolved, is we have taken those steps where a conventional formwork was there. In the 90s, we marginally improved that. We went with tunnel formwork, which is still one of the fastest systems when it comes to building. But very unique niche kind, you have different challenges. So we tweaked it further. In 2002, we took that call that whatever L&T will do in building construction will be aluminum formwork, right? Not the beam column frame system, but we will pour everything in concrete. Now in today's world, that 2000 call would have been questioned a lot in terms of your green, in terms of your sustainability. And we will talk about that probably briefly. But the idea was, we felt in that 2002 to 4 time frame that whatever construction we are doing, the demand is going to be accelerated. And we cannot keep doing whatever beam column we are doing, because the block by block construction may not be feasible down the line. And that was tapped. I think we are blessed with very visionary leadership, and they said this number of people, whatever we operate, we have to get out of this block construction. We have to get out of this plaster and internal plaster and external plaster, and that's where that aluminum formwork system evolved, right? We were one of the first ones to bring that in. And the same cycle continued in 2010 to 12 time frame. Again, the thought process became is even the aluminum formwork in 2020 onwards, we may not be able to do because of the number of people, number of activities, whatever, and we switched to precast construction. If I have to put the numbers behind it now, this is all our in-house internal numbers. You take projects, we have compared aluminum formwork project and another precast construction project in the same vicinity at the same time frame. Both projects started operating together. And very broadly, if I have to put in, I need about 5.5 man days to pour 1 cubic meter of concrete in our projects, right? Some other clients may say, no, I do it in 4, that's fine. You can do it in 4 in your system. But if I have to have L&T way, I have to operate L&T way, I take 5.5 and we have given the split. If I do a basic precasting, and this is why that 2010 we started thinking we have to do precast, I need about 3.5 people to pour that same cubic meter of concrete. If I do slightly advanced, I'm not even saying state-of-the-art Europe, if I do slightly advanced, some circulation, some automation, that 3.5 changes to 2.5, right? Now, if you compare that 5.5 to 2.5, yes, it's drastic improvement. But the point that we started really noticing down the line after 2-3 years of precast is the 5.5 is at site. The entire 5.5 is happening at that project site. If you're doing it at the 10th floor or if you're doing it at the 40th floor. The 2.5, only 1.5 is happening at site and balance is at factory. So comparing that 5.5 to 1.5, 70% to 80% of my activities are moving to a controlled factory environment and only balance that 20% I'm operating at site. Now, why this is important? Because from 2020 onwards, last 5 years, we have seen that manpower and managing manpower challenges are increasing day by day. So now if I have to commit something saying, okay, I'm going to do this X activity and I'm going to need 50 people at site, to manage that 50 people on site and promise the client saying I'll deliver in 6 months is becoming difficult. But out of those 50, if the 35 are in somewhere in the factory where they stay at the factory, they come same day, same environment, working on the ground, it's much, much easier. Our own retention rates are much, much better in compared to factory environment. So what our learning has been the last decade is off-site construction. You move whatever you're doing, you move it to a controlled environment. The assured delivery is what we are focusing now more than the speed of the construction, right? Earlier when we started precast, it was your rapid construction, you build faster. Where we stand today is you promise your client that I'm going to give this to you in 12 months and you try to give that in 11 months to 13 months. Where if I have site activities, that 12 months is, no matter how much I tried, may become 14 months, 16 months. Right, so with that then why we did precast, again we said we want to show, and we have done a couple of buildings to try ourselves to show where the technology capability is. We did this 2 years ago, one building, what that building you see is a real building, a 12-story tall building, about 96 flats, and it became a Mission 96 where 96 flats were delivered in 96 days, right? And this is that assured delivery, what we are talking about is a 3-day cycle was planned. And right from the first floor to the 12th floor, each floor was completed exactly in 3 days, dot, every floor. Yeah, we were tracking that in hours, not days. If you see this aluminum formwork now, and our own sites itself, first 2 floors are going to take time. You set up the formwork, you find the crux, you find the issues, and if your cycle time is 12 days, guaranteed that first floor takes 25 days, second floor takes 20, then you come to 12. Once you go 10th, 12th floor, your aluminum formwork also, you can hit a 6-day cycle. We have done that in our sites. But that continuous sustenance. But here, right from day 1, 3-day cycle was planned. Whether it's 3 days or 4 days, we are taking now pride that I will give that guaranteed delivery and I will deliver your building to whatever is promised, right? Same way, very different system now, beams, columns, hollow core slab for commercial. We did this about 2 months ago. But what you see on this slide is about 360 car park, 1.4 lakh square foot built up area, ground plus 6-story, and this was completed in 41 days, painted, right? And that's the speed, that's the delivery. We planned 43 days. It was called Mission 45 with the 2 days of buffer, but we finished in 41 days. But where next we want to take it? I told you that off-site construction. So we said again, going forward, if I build this parking again, I'm going to paint those elements in the factory. Why do painting at site? So we did a couple of elements where they were painted at factory, they were shipped to the site, painted, ready. You just put it, install it, the connections are detailed so that there is minimal damage in painting, and we can finish the buildings. Now where we go, a precast, now we have scaled it up. We have now, of course, taken this at that time was one of the largest project, but we are about handing over that project in Navi Mumbai for mass housing. These are about 7,500 flats for social housing. But these are ready. Whatever pictures that I show you now is we have taken up to the scale, right? We have about 60 buildings ready. Those 6,500 flats handed over. And at scale, what you see in the pictures is about 2.5 years of work. Total precast except the foundation and the first floor, and buildings are ongoing. The first phase was about 12-story building. The next phase, this is about 17 and 19-story building. And we are extremely comfortable in terms of delivering large-scale housing projects using this precast construction now. And if I had to summarize in the plan, this is what was planned, and we were looking at about 30 floors per month using the system, about 8 flats per day. And we are doing about 28, 29 floors per month now on this project, and it's getting delivered exactly the way we planned. Now this, we call it a social housing project, but architect Hafiz Contractor was the architect, and from day one they were clear that we want our signature, we want to deliver a better product inside out. So even the elevations if you see in the pictures also, there were bands, grooves, and usually there is a stigma behind precast saying it has to be modular. It does inside. Outside treatments, there are ways, there are engineering where we can use the same molds and still change the elements, do the tweaking. It has its own requirements, but we were able to manage that and do it. And kind of on this scale of projects, the building itself or the unit itself becomes the modularity. You don't want to do any further modularity inside the unit as long as the units are repeating. If you see this floor plan, each quadrant is repeating, and then each quadrant is repeating many, many times where we can afford to do this. We do set up site-based factories. We are not there where we do centralized factories, but this is how the site-based factory look. A lot of clients ask saying temporary factories, what would be the quality? So when we set up, it is as good as a permanent factory. We just call it a temporary because the land is clients and the land has to be handed over. But large factories, they operate a lot of detailing, everything we are doing in-house now to control the cost, to control the quality, to control the detailing, but all our molds, everything are being done in-house. If you see the right side bottom, that's the pre-finished. Again, the next 5 years we'll be probably looking at you paint, you putty. We did just one building where the doors, the windows, the electrical cabling also was done at factory. And 2 units went to the site, and we even connected the electrical wires and turned the lights on the same day. So that's where we are moving. With that background, we think we took up a next project now, which is ground plus 23-story building, about 11,000 houses. And it's a repeat order from the same client, and this time they shrunk the timelines, right? Because they have now seen precast, they got the taste of it, so they said, yeah, this is the timeline. And at that timeline, the kind of factory we set up, this is one of the largest factory that we have set up to date, about 3.3 million square foot of built-up area per year. At that scale, at that timelines, the precast came marginally cheaper than aluminum formwork, right? And this is where the technology scale comes into picture. If you tell that I want this 11,000, which is about 7 million square foot, in 42 months, the number of formwork sets that I would have to deploy to complete that in 42 months, that cost is marginally more than setting up the factory and doing it in precast. Of course, whatever the division and all math will come, but this is where we stand. We are doing different things, but the focus, if you remember the first slide that I showed, mechanization, right? So the first factory that we built flat elements. This is one of the first hydraulic automatic battery mold, which kind of cast all wall panels vertical, both side mold finish, no manual finishing. The green one is the concrete delivery system. So the concrete shuttle comes from the batching plant and the concrete gets poured to your wall panels in under 6 minutes. There is no transit mixer, there is no half an hour waiting and mixing and everything. no manual intervention in between. We are getting cleaner panels with both side finish, paint ready, no plaster external, internal. And then we have done now where it can be scaled. So of course this was our first building which we did. It's been standing there for 10 years. Something similar we are doing. This was in Bangalore, large scale. But what you will see, the engineering, once the buildings are finished, the end user doesn't feel any different in terms of the look, touch and feel. The same grills, the same chajjas, the balconies, inside and outside. You will get the same flat. Even our own engineers won't be able to find out where the joints were, right? Coming to the commercial sector, again, we've done dabbling in that. Now residential has been perfected in our mind. This is a hostel building in Tirupati. It started as a ground plus 3-story hostel with 2-story extension, because the client at that time thought that I won't be able to open the hostel, so I will add the 2 floors later. The way we built it, they said at the middle of the project saying, you give me the 5-story building, and we still open it at the same schedule. This is in Reliance Jamnagar, total precast buildings, long 250-meter electrical room. We did slightly different seismic zones, and also the elements were done where the beam columns are still cast monolithic, and they have stitched at a different areas. In the same project, 11-meter tall, 1,000 columns. So we converted that to precast. Vizag, we have a substation building that is a small portion of the project. It's a 2,000 crore project. The building is only 35 crore, but it works as a heart of the building. So they said, we want this faster. So all these substations only we converted. And the last substation was built, this is the building, in about 2.5 months, which used to take about 12 months in that region to bring people and install. Stadiums has become a norm, so we are doing this Varanasi Cricket Stadium now. This will be handed over in March, very unique Damru shape and all. And then the last bit is hybrid. So wherever, we are not in precast business, we are not in technology business, we are in the business of building buildings. So wherever that it makes sense to do, we keep looking at it so that the speed will improve. And if you see this left-hand side picture, it's 150 villa, and they have this English look where the cap is pyramid shape, and it's a double story. So you have to shore 9 meter, and then you have to do the pyramid ones. The cast in place was taking 25 days. We said we will do only the caps, rest of the villa can continue off-site at the same project, precast on the ground, 5 caps each days. 8 to 9 hours we are installing the cap instead of that 27 days. Right? And this is where we keep looking at it. Right side picture, again left side picture is our N-mile new T2 airport that we opened up, 15 kilometer of compound wall. It came in precast, but the typical plank systems. So each bay had 4 planks. We said, why 4 planks? We will do 1 panel, 1 finish, no joints with your lettering. And your 20,000 elements became 5,000. And that wall was 15 kilometer was done in precast in about 6 to 8 months. Hybrid, we are looking at steel now, facade elements, whatever that you can finish. Again, blockwork plaster that takes 3 days. We will finish in steel in 2.5 hours, 3 hours. Toilet pots is another business that we will come to. We have done 2-3 residential buildings where what you see in the picture, everything is finished fully at the factory. It's already there inside that cubicle except the door, and then we built around it. We have done the same thing in commercial as well. And except the weight challenge, we can handle everything, right? So with that flavor, I know it's rushed, but time was short. We want to keep it short. The couple of other last slides, I'm not going to run through it, but I will give you the half-a-minute summary and close it. Where we stand today with precast construction, whether it's a residential building or commercial building, the way we have now looked at it, engineer and design, the usual 2 questions that come in client's mind is one, seismic detailing and earthquake, how it operates in design, and second, of course, how your joints are operating. When it comes to seismic detailing, we are 110% confident. We have done various test programs we can discuss out of these forums. We have multiple approvals. There will be a new code that will be coming where we will be adopting the system, so there is a backup and basis. We are confident. When it comes to joint, I'm at 99%, right? But when I say 99%, I am treating those flats as water tanks. each flat is getting flooded with 1 inch water, not just the toilets and kitchen, the entire flat. We look at it, we look down, we check it, we look at the external joints. Where we stand today is the precast for residential is, one, is not leaking, it has seepage, there is a slight difference. Second, it is less than conventional or cast-in-place buildings, right? With the theme of the conference, this is where I will conclude, is how that contribution to sustainability in terms of precast, what we feel, is purely the low-hanging fruit is wastage reduction, right? And we have been monitoring our own data now. Everywhere it is obvious, but one of the biggest thing is your steel reduction, concrete reduction at the factory level. And there is 30, 40, 50, 60% reduction in terms of wastage, where we are now started counting it towards the tender itself to control the cost. So with that, thank you very much for your patient hearing. I know it was not exciting as a high-speed railway, but hopefully something different. So thank you, appreciate it.
Hello. Hello. Amit, it was equally exciting, very much exciting. In fact, today need is precast, and we cannot afford the construction agency to remain at site for a very long time. So unless they do precast, unless they work in factory, one cannot achieve that. Amit, there is one question for you from myself. Your project at 96 flats in 96 days. In fact, I've heard it earlier also, and I have myself given many awards in different forums, in ICI, in CNCR. It was very impressive. Now, if I'm not wrong, you mentioned about 750 flats in 2 years. Why it is proportionate? Why not in another 96 days? 750 flats in 2 years.
Yeah. So 2 years actually 7,500 flats.
7,500.
But the question is valid. Yes. The 96 or the 3-day cycle was done to showcase the best of that technology. Just for that one tower, if someone wants to pay the premium, my 6 or 7-day cycle will become 3-day cycle, because bosses came one day saying, tell me what best you can do. We said, if you give me more resources, I will do much better. They said, okay, how much, what more you want? I said, you want double cranes. And we'll go in detail at the top. Usually we operate 1 crane for 2 towers. We operated that tower using 2 cranes on 1 tower. Right? So resources were more, not in terms of cost. The crane machine months were still less than what we would have used, but 2 cranes were required. The duration saved, the machine months are still lesser, but more resources. Second, if somebody comes and tells me that, okay, now you give me all 12 towers on going 3-day cycle, my factory size becomes 3 times. It may not be viable.
Yes.
Right? 1 tower I can do, I can channelize the resources, but technology will do that 3-day cycle. What we are doing, the 7,500 units though, is a consistent cycle of about 6 to 7 days per floor, where your conventional construction will be at best 12 to 15 days. So you still get that reduction. 3 is a very aggressive and drastic number. But conventional net, like I said, the rapid construction, we used to say ultra rapid construction, but we have stopped that. Right? We are now focusing on that assured delivery, because what has happened, 2 things. In our experience, 5 years ago, we were building one building, let's say it takes 18 months to finish the structure and 12 months to finish it. Today, that 18 months, we are finishing the structure in 6 to 7 months. The finishing has gone from 12 months to 18 months. The ball is in finishing court. This is why we are saying now going forward we will be looking at pre-finishing. It's not for my fancy. That's the need. I'm not able to find people who will paint. I'm not able to find people who will fix doors at sites. It's becoming...
Anyway, thank you very much. Any other question?
Yeah, so it's not like if you tell me that I put everywhere 2 cranes, it's not possible. So this is okay, 3 days. I'm not committing any client saying I will finish in 3 days unless somebody wants to pay a significant premium. But yeah, usually you're right. People say, oh, I deploy 4 cranes. You do more, but it's not. Efficiency comes down combination. Yes. So multiple things to look at.
Yeah, there's the optimum period. Yes.
Sure. Thank you.
Thank you very much. And our next presentation is now Mr. Anjane Prasad from Metri Consultants. Now I will speak on concrete technology for high-rise building. Sir, 20 minutes. Thank you very much, sir.
Okay. This set I have to operate only here. Okay, that's fine. Right, good evening to one and all. That was a wonderful presentation from my friend Mr. From L&T, Mr. Amit Bade. Right, so precast is the order of the day. Even in Hyderabad, we have a 6 basement plus 38-story precast construction happening, and it is being built by my home. And I request one and all to go and look at it. It's all with the 12-meter clear span hollow core slab and wonderful precast columns, long span structures. A beautiful way of the projects are coming up. Hyderabad is a hub of precast construction, and a number of precast companies are there catering to the outside as well as the inside. Like my home has set up their own, and similarly Arabindo has set up their own, and then have been developing their own precast structures to meet their own demands. Right? Thank you. Now coming to, well, I'm a precast consultant too, design the buildings, but now Subramanian Garu has forced me to talk about concrete technology in the tall buildings. When I said I will talk about tall buildings since I have been designing it, but he said concrete. So ICA is for concrete, so concrete, we have to talk about concrete all the way. Right. Right. Now, we have been seeing that the buildings, whatever that we are building, tall buildings, are predominantly started with the steel structures. Then it went on to composite construction. Nowadays, we have come down to concrete a lot. Like what you are seeing, Burj Khalifa. Burj Khalifa is about 160 stories, it is concrete. Thereafter, it is steel structure, right? The 160 and 80 stories criteria is basically like at the top level, it takes too much of deflection. So they thought to cater to that particular deflection and the movement, for that particular purpose, they went with a steel structure above 160 stories, right? So we'll move on to understand. So in order to go to the concrete technology into the tall buildings, first of all, I shall run down how the buildings were built earlier, what is the concrete grade used in that. Then we'll come back to what is high strength concrete, and then move on to high performance concrete lightly into that. Now we all know that yes, concrete is the way that it is coming up. It is pipe proof. That is a fantastic way. I've seen here in Hyderabad, Phoenix is the developer who have recently built a 41-story composite construction building. Okay, it is all with the core is with concrete, but then they have the steel columns and steel beams. But then they have applied the fire paint to the steel beams and the columns, okay, which is costing about 2.5 times more than the basic structural steel material. So this is the way they apply the corrosion resistance paint and then the fire paint. Fire paint is so costly, and they do not want some sort of a cement-based material, but they apply the intumescent paint, which is pretty costly. But then they achieved the timelines in terms of they have finished the building in 1.5 years, 41-story building. There is a beauty of coming up with a composite construction. But why did they go for the steel structure? Means it is a pace and the speed at which they want the building. They want the building, instead of 5 years, they wanted it in about 3 years, or even reduce it by 2.5 years, because they already have the clients ready to occupy. So they will get the rent for the rest of the 2 years. Okay, is what they look at it, and still they thought it is profitable, and then they went for that. So the order of the day is speed of construction. As Amit has shown it, like in the form of precast, the speed of the construction, even the composite construction, and nowadays precast construction, right? My home has also gone in that manner. Like they were there with conventional construction. Thereafter, my one, now they are into precast. Okay, this is how the concrete technologies are evolving and then driving the speeds. But then the concrete trunks are also driving now, the heights are increasing and all that, okay? So with the heights increasing, then the concrete demands are also increasing. We will look at the Shears Tower, one of the fantastic high-story building designed by our great engineer from Bangladesh, Fazlur Khan, okay, where he built this particular building with a 3x3 grid of 9 grids, and then built this particular building, which is called as a bundle tube, right? And then this building is a 75 feet wide, arranged in a 3x3 pattern. But then into this building, what they have done is hardly during those times in 60s and 70s, a 442-meter high building is built with just a C40 to C50 concrete. During those days itself, they have done for 440-meter high, but they achieved it with 440-meter. But it is a predominantly a steel structure, but encased in concrete. Columns are encased in concrete, but still they went with that sort of concrete to do that. And then we see, I just run through some of the towers, such that we understand what is the height and what is the concrete gates they have used, such as correspond to the loads. So it's the Princess Tower in Dubai. Again, it's a 101 story, 413.4 meter tall residential skyscraper with a floor area of about 171,175 square meter, right? And they did also use C80 to C90 concrete, C80 predominantly for core walls and columns, increasing to C90 for the lower levels, right? This is the Princess Tower in Dubai for 413. But if you just see Sears Tower, already 442-meter tower, earlier in way back in 1970s, they already used C40 to C50. But here are the people who have now, the dimensions have increased. They have the central core, but then they have the peripheral columns. Okay, these loads demanded that they have to go for the C80 to C90 concrete. We have this 23 Marina Tower in Dubai, which is actually 88 floors, but they say 90 floors. It's a different this thing. And again, this is like, you can see that you all the way have the peripheral columns, okay, which is predominantly getting the resistance and all. The internal core is not attracting much into the lateral story, but it is predominantly a load-bearing RCC wall structure. Again, this is also taking a concrete of about 45 grade, and for the lower columns and all, it has come down to C80. As it went up, it has taken the grade of concrete as about C45 grade, okay? Only at the lower levels, they have this particular thing. So this is the ACECON Tower, again, 72-story tall octagonal tower. This is a very peculiar shape. In Dubai, the beauty is that every architect can come up with their own model, and then the sheikhs like it very much. It has to be different from the other building, okay? It has to be different. Wallah, it should be different, not like the other. So architecture is like an architect's paradise. They come up with the different shapes, right? So there is a beauty in the architect. The towers in Dubai. So here the high strength concrete that's specifically used about C80 grade for the lower columns, and shear walls and C45 grade as it went up, because the loads are reducing as they go up into that. This is Mumbai again. This is a 300-meter tall tower. It's a residential apartment, okay? And then it has also used only 52 MPa in the lower parts and 42 MPa higher for a 300-meter tower in Mumbai. Fine and sufficient enough, but then they used a high-strength concrete because it's very next to the sea coast, and then there are certain advantages of giving good durability and into that. We go on to look at Burj Khalifa, the latest tall building tower. Well, it has the structural system is a triangular core shear wall buttressed by 3 double walls. This is the beauty of it. Along the corridors of each leg of the plan, the floor slab is a 200 mm flat plate. Calculations of shrinkage and creep of vertical elements were done to develop a differential axial shortening matrix, right? And they have also done this deflection a number of times, and then there is a lot of correspondence between Haider Consulting and Skidmore Owens from UK, and then they got to a point whereby they have agreed on a particular deflections and all. Now we move on to Cayenne Tower, Dubai. This is a wonderful structure where the architect has taken a box and then twisted it, okay? Twisted it, and then the shape has come like that. Okay, and then there is even though he has done a simple twisting, but it is so difficult for the construction purpose, first of all, even though design is being put up by the structural engineer in an easy manner with an inside core and then the peripheral columns around the 90-degree twist that it has happened. There is a 75-story skyscraper in Dubai, and it is a marvel of its construction and demonstrating what we can plan, can be dreamt of and can be delivered. It's a beautiful shape that it is there into that. Okay, then yeah, this is again, this is how you can see during the construction, how it is going up into that. Again, these people have also used the concrete grade, okay, from about C40 to C85. As it goes up, it is only C40. Lower down, it has got about C85 into cores and frames of it. Right? I will not run through all that because even though there are certain things, time is a constraint, but the PPT will be given to all of you. Then I was looking at it, is it the only building or there are other consultants also who have twisted the box? Then I was fortunately looking at so many buildings are there in the world where they have done lots of twisted things to that. And I'm quite amazed to look at, there are so many architects, so many structural consultants who have delivered with lots of twists to the building, right? There's some of the information that I gathered, right? Then I will move on to JP Morgan Chase Plaza, Houston, USA, where this is a 5-sided building, okay? It's like normally we have 4 sides, but here is an architect who have made the 5th side also with a cut in the front side, right? So this is a wonderful building. It's a 75-story composite structure again with an open tube composite perimeter frame. And then its height is about 305 meters. It's a slender 5-sided building. At that time, it used to be called as, right? And then they had a beautiful entrance in the front, which is like again, a 5-story entrance. What they have provided in the front is a beauty during those times. Okay, and then there is a 26-meter clear span in the front with like a ruptured tube, what they call. And then they have done some extensive tests on the wind tunnel tests and all that. Okay, and then they have provided about the composite structure. This is how the building is during the construction. You can look at it. And some of the plans of the building. Okay, but even then, what you can see here is because of this particular thing, they have provided the shear walls adjoining the lifts and all that. It has given the stability to that, even though the perimeter columns are taking the brunt of the to give the stability to the whole building, right? Some of that. And then the concrete strength that they have proposed for the 300-meter tall building is 52 MPa for the 56-day strength. This is something that we have to understand that it is 56-day strength. Sometimes the architects, the structural consultants also say 56 to 90-day strength. Because as the number of floors goes up, the total load will not come right on the day one, okay, as it goes up. Then they say that, yes, I require so much strength at 56 days like that, and then it's not necessary to get the strength on the 28th day, okay. So this is how for most of the particular thing into that. But then having done that 52 MPa concrete, how much time is left? 5 more minutes, right. 52 MPa concrete, it has a modulus of elasticity of approximately about 39,330 MPa. The basic factor is that the high strength concrete gives high Young's modulus, which is good for us to take care of the deflections, okay. That is a main factor into that. And as well as the drift that will take care of into the giving the strength. So the damping, it is about 18 milli-Gs for a 10-year occurrence for the JP Morgan, this thing, after they conducted the tests and all. So instead of, they have provided about 2%, whereas 1% is a normal thing for this particular thing. Then there is in this building, they have seen that there is an axial shortening happening, right? To account for this, then what they have done is at the roof level, the columns at the end of the 26-meter caisson were placed 2.5 inches higher. This is something that one has to take care of as they go up. Axial shortening happens. So they have taken care of this by placing it higher, 2.5 inches higher. Okay, this is something that they do the calculations, what happens to that. This is done even in the Burj Khalifa also like this. They have done that and then increased the heights of the perimeter, this thing into that. Then rheology of concrete, I think this has been discussed at so many presentations have been happening here. It's basically the flow and deformation. I will not go much into this. Okay, all of you know about it. The factors influencing rheology is mixed proportions, shape, size, and texture of aggregates, grading of aggregates, use of admixtures, water to cement ratio. We are talking about it, but the rheology is such that we have moved from this slump factor of measuring the cone to the flow, whereby we say that T50 means how much time it is taking to come to the ends, by about 2 to 5 seconds. And for Burj Khalifa, we have gone for about 600 mm is the flow that it has happened. Right? A high slump value of 100% in the conventional democracy is also an indicator of high workability. Though slump flow is more precise measure for SCC. Predominantly, we go for the SCC into the high strength concrete. Right? I will just skip this. We all know that all these buildings are provided with the concrete. This is one small information to you. And this is the information that we have for the tall buildings and all. As Indian standard provides for ordinary concrete M10, M15, M20. Standard concrete is M25, M30, M35. High strength concrete, it simply says M60 and above. Right? Having said that, then normal strength is 20 to 50 MPa now. High strength is 50 to 100. Ultra high strength, we are going to 100 to 150 also. This is the order of the day. Ultra high strength, we are going ahead into that. Till 1950s, we said 40 MPa is high strength concrete. Now by 1980, we are saying 70 MPa. But Burj Khalifa has applied only about 80. Okay, why they have not even gone to 100 is that when we have conducted the test, we have seen that the concrete is breaking suddenly, abruptly. So that's why we have seen that the admixture is doing the mischief by making the concrete brittle. Okay, so crossing 80, it is while we are doing the testing, it is suddenly breaking. So we thought it is not good. So we wanted to restrict there up to 80. We have provided that. So the breakthrough research is that we have the development of high strength cement, research in chemical admixtures, use of mineral admixtures, particle packing theory, improved understanding of hydration. And we all know that the mineral admixtures are these are the things. I need not say, all of you know about this, Pozzolnik effect. And they are the colors of those Pozzolnik different admixtures. I'll try to skip this one, silica flume properties, because some of these I don't see the need of talking about it, is already covered it. Give me a little bit of time. And then, yeah, pumping aid, right? So these are pumping aid differs as an admixture used in concrete to enhance its lubricating properties and reduce the segregation, thereby facilitating smoother flow and decreasing pumping pressure during the transport of concrete. This is the main important point where we have these different superplasticizers, various pumping abilities that they give also are mentioned there. And the main difference between normal and HSC concrete is this, where as I'm saying 28 days strength is what we see, there it is say we are talking about 56 to 90 days. And water cement ratio is predominantly at 0.3, and then we use the admixtures into that. Right? I just give you a simple example of a column. I think the time is up. Yes, right? I will just end here, even though a lot of material is there. Let us look at the concrete grade 40. I'm using 800 by 800. I'm getting a capacity of 14,458 kilonewtons. The same thing if I'm increasing my strength and decreasing my column size and how it is coming, that still I'm getting an increased size. I just made one small table over there. Okay, but after crossing 80, I think I have to increase the size, and then I look at this particular. So that means higher the strength of the concrete grade, right, and the column size can be reduced is the bottom line which we are looking into. Thank you very much.
Thank you, Mr. Prasad. A wonderful presentation showing so beautiful building, tall building. Sir, I want to ask something. Now, we have been talking about tall buildings. Now it is not only tall and super tall buildings. And in Delhi, so many structures are coming, Delhi also, tall buildings, and we are going for composite construction. And you also mentioned your composite construction, though all the buildings are shown are in concrete. Sir, do we have really Indian codes available for constructing tall or super tall structures as composite construction? Is it not a challenge for us today?
We only have the tall building code at the moment, but wherever our codes are not supplementing the information, and the code also says, IS code also says, please use other international code information and go forward for that. We are predominantly using the ACA code and the British code to design these tall building structures into that. Okay, but we are somewhere near to that, but now the tall building code and the composite construction also, we are giving that information. The new code is going to come shortly.
Thank you very much, sir. Any question?
I just entered, but I'm Dr. S.P. Anchuri. I'm an architect and structural engineer practicing here. There are some people who came from outside while coming from airport to, they might have seen the tall structures. What we talk about the commercial buildings, we have a core and other thing, whatever we theoretically do, and we are trying to achieve those things. But if you take the residential sector, that too particularly this part of the country, we don't have core and those systems because they are just excluding like an individual, apartments because of some reasons, that may be Vastu Shastra, that may be any other reason. But even if you go up to 60 stories, we find no cores and no, why that is happening? Because you're, Hyderabad-based, you're observing that. I'm facing those challenges, I'm worried about that. And so, what is your say on that? Thank you.
Now, to answer your question, our tall building code, which is 16700, 2025, now covers the height up to 250 meters. Right? Now, when the people build this Burj Khalifa also, which is 828 meters, there is no code across the world. Okay? Let it be American code or anything else. But
not core, I'm saying, lateral resisting system itself. I'm just taking core as only as a lateral resisting system. But when you take this configuration, so because I have to interact with a structural engineer, that interaction is not happening as per the requirement of the even course.
okay. Right. Yes, Anchuri has moved from structural engineering to architecture. Now he is talking like an architect. Fantastic. Right. See, basically, I worked in Dubai for a long time and then returned back. There the architect comes up with his plan and throws it on my table saying that, Prasad, I need your structural system. Right? And when we give the structural system, then he comes back and then, can I have some tweaking changes? If I have these changes, if you say anything no to my changes, you have to be very sure. Otherwise, I'm going to change you. Like that, we used to have a good, useful discussion and then come on the structural system, explaining it nicely into that. Now, coming back to Hyderabad, the way the things are going now, where the Maiwan construction, what the people call, what we call it as monolithic construction technically, okay, it is all RCC walls. Okay, these RCC walls are load-bearing RCC walls and they are also shear walls. They have a tremendous lateral resisting system, and for Hyderabad Zone 2 earthquake, even though it is, because the developers are adapting that for their construction ease now, because there is no need of putting the scaffolding and other thing for the 50-meter building or a 50-story building or 60-story building. Totally concrete, totally RCC walls, and a very good, robust RCC wall structural system against the lateral force. It is highly good and fantastic. Anyone going for the Maiwan construction, providing that RCC wall, I simply say, go ahead and buy it. It's a very good system into that. Okay, and RCC frame again, we need to have, because the code again says, please get it verified through a proof consultant. If there's one consultant have done it, other consultant have to check it. Both of them have to take the responsibility of giving that structural stability assurance. Once that is done, this is okay. I'm also doing a lot of peer review and then doing that. Yeah.
Last quick question. As you are from Gulf, the temperature there is poor, and even Hyderabad has about 45 degrees. How do you solve this thermal insulation? Because it's a problem of, and we are talking about sustainability, we are talking about the carbon footprint, carbon neutrality, and this aluminum formwork. It's a contradiction going on in the codes.
Yeah, to answer that question again, if there is a cross ventilation to a bedroom, right, you have two windows and opposite sides of that, then the wind will flow and the heat effect is not there. Okay, and except for the terrace floor, where in the Gulf, they provide the insulation on the rooftop, okay, and then the waterproofing. There they provide about 50 to 100 mm polystyrene insulation to reduce the heat. It makes a difference of about 4 degrees centigrade. Systems exist even now. That has to be provided here to reduce the heat. Otherwise, for the RCC walls and all that, provide cross ventilation, heat is reduced. Thank you very much.
Thank you very much, and thank you, engineer, doctor, and architect Anchuri, for asking the questions, and the replies are adding more knowledge to all of us.
Questions will be much more information.
And before I invite the third speaker, let me, after this session, we'll have award ceremony followed by cultural program and dinner. Please don't go away, attend all these. Now we have third presentation again from a wonderful speaker, Engineer Anthony Sung from Cemented SEA Pte Limited. He will speak on hyperbolic pore blocking ingredient for sustainable concrete structures. Aye, sir, please come. And please try to maintain 20 minutes time limit, sir. Thank you very much.
Actually, cultural program we want to cancel because time is not there, only for dinner.
To next.
I just put it on top. Yeah, okay. HDMI. Connection total easily. Yeah. Hi, good afternoon, sir. Good afternoon, ladies and gentlemen. Thank you very much for taking time until now. Quite late. We are running over time. Anyway, I would keep my presentation within 20 minutes so that while not taking too much time of yours. First, thank you very much for giving me this opportunity to introduce our system to the floor here. My name is Anthony Sung from a company called Cemented. I'm based in Singapore. Originally, we are Australian companies. Today's topic is to identify sustainable system for water retaining structures, such as basement, tunnel, roof, landscape podium, water tank, etc. Now, concrete is a very common used product in construction industry, but we have to realize that while we need to waterproof this concrete at place when it is necessary. Now, the function of waterproofing in this water retaining structure is to separate the habitable and proposed activity from water leakages. If water leaking into your structure like roof, basement, or swimming pool, water leaks out, it causes inconvenience. But the most important thing is that when we allow this water to passing through the reinforced concrete, reinforcement inside would be subject to corrosion. Now, all concrete get wet because concrete absorbs water. Concrete, no matter how good, even including what this morning a lot of speaker has been mentioning about high performance concrete. Now, but unfortunately, high performance concrete, when used in these locations like marine structure, very deep basement, or roof, it sometimes might not be totally function well. Because if you still have water consistently going to this high performance concrete, this high performance concrete still would absorb water through the weak action. Because this concrete, no matter how, even in today's technology, we are very, very difficult to produce a concrete without capillary. It's the capillary draw this moisture, not leaking, the moisture passing through the concrete. And this moisture is a kind of water. It would still wet your reinforcement and cause this corrosion ultimately. Later, I will show you some of the projects which has been using high-performance concrete, but is still having this moisture affecting their structure life. This is why even water-retaining structure using high-performance concrete, you still have to waterproof it in order to fulfill their function, as not allow water to passing through. So the question is that, well, how to choose a sustainable waterproofing system? Now, traditionally, we have been using barrier, membrane, coating, trying to separate the concrete in not touch with water. But we all know that while this material have a lifespan, when their lifespan expire, we have to replace it. Now, so they might not be really called sustainable, because once you need to replace it, we are actually producing a lot of construction debris. You have to remove your protection layer, go to the membrane, and then you have to replace the membrane, and then you have to use cement again to protect this membrane. Now, this is only time when you have access, like roof. If, unfortunately, it is a substructure in a basement, your membrane could not be able to replace, because in most cases, these membrane are actually at the external side, at the underside of your slab and wall. There is no way that you can go back to it. So you just live with it. Now, to choose a sustainable waterproofing system, personally, I would say try to avoid to use protection layers, because most of this material have a lifespan. I would suggest to use something like what I'm going to introduce, integral system. But how to choose a sustainable integral system? Usually we mention about this integral is like something to add into the concrete. So we have to use a material non-toxic. Now, toxic material is not sustainable. So when we produce or manufacturing these chemicals, we need to use non-toxic material first. Second, the lifespan of this produced chemical should be able to sustain. So to look for a product that has been used in the market, having a proven track record is also important. So today I would recommend a product called HPI. In fact, HPI doesn't appear in this market until I think around 30 years ago. It's when we supply this integral system to this Suntec City in Singapore. The consultant requests us to take out the product name so that while it is fair to everyone. So we have to produce a generic specification. We checked with our consultant, Professor Adam Neville. So he suggests that while waterproof concrete, sustainable, it needs to be fulfilled two criteria. Doesn't absorb water. Second, if water under hydrostatic pressure could not be break through this chemical barrier. So he suggests to use a term called hydrophobic pore-blocking ingredient. That is to describe the product. Now, this product 30 years ago, or actually 60 years ago, we have been using it in a lot of infrastructure and building. Now, just to mention to you, sustainable, I just mentioned that while we need to have this track record. Just 2 years ago, a developer owner, it's a hotel in Perth. He requested, which we supply the waterproofing for the roof 50 years ago. It has never need to replace, and it was functioning well through these 50 years. So he suggests that he want to take a core or some cores in the structure to prove that this material is still inside the concrete. So he employed a consultant he trusts to do all this, and the report came out that our material, the hydrophobic material and the pore blocker, is still inside the concrete. So this is a project which we done 50 years ago, and now confirmed by the developer himself. Sheraton Hotel in this Perth. So this is what we supplied last time. We also have a lot of other projects, but this one is that the owner, he himself want to prove that the material is there, despite that it never leaked. There is no leakages. He's very happy with the performance, but he want to prove to himself that the material is still there. So he successfully do it. And we call our product sustainable. Is actually, we are the first product in Singapore as an admixture approved by the Green Board in Singapore, Green Product Board. And we are the first one. They approve us, it's not because they visit our factory, they check our formula, we don't have toxic material, we use recycled product, and so on. He actually based on life cycle, because we gave him a list of projects, all 30 years, all at least have 30 years history. So they do assessment on all this track record and prove that our product is really sustainable. So he gave us the first green certificate in waterproofing and mixture in Singapore. And we have project, which I will show you as a sort of like track record, which we did 60 years ago, or actually should be more than 60 years ago. In 1962, in Adelaide, we put a pipe chair in the short pan. It is still there and performing very good. Now this is how our material working. When we put our chemical into the concrete at the batching plant, once it mixes, the chemical start to react with the calcium in the cement and form a hydrophobic material. This material would coat the capillary. This material is changing the contact angle of the water molecule in touch with the surface. So this contact angle would be much bigger, and the water would not be absorbed into the concrete by this capillary force. Now, as you can see, this black dot, that is the pore blocker, which we call it. So when you have water in touch with the concrete surface, you see that the contact angle is much larger, so it would not be sunk in by the capillary force. And even if it is subject to very high hydrostatic pressure, the water would push this pore blocker together to form a physical plug in the capillary. So that is how this so-called HPI works. Now maybe I showed you the concrete like this. Now there's normal concrete on the left-hand side, on our right-hand side of mine. When you drip water onto it, it sucks immediately. But on the side of this HPI concrete, you drip water onto it, water would not go into the concrete. So this is how the product works. Now, the HPI product provide a live waterproofing effect and reduce this waste to landfill compared to traditional system, which have limited lifespan and often have to be removed and dumped in the landfill before you can replace the material. Now, this, I have to emphasize, is only when you have access to it. If it's an underground structure, a tunnel, forget it, no choice. You cannot replace it already. That's why when we walk to some of the underpass, tunnel, 20, 30 years old one, you start to smell the dampness. And later you might see some of the dampness actually exit on the surface of the concrete. Now, this HPI product improves durability of the concrete and the structure, therefore reducing the need to replace the material and repair material. Now, this HPI product, one good thing is that while it do not need any external protection like membrane or coating and whatsoever, all these projects, which I showed you later as a project reference, are just using the HPI product. No membrane, no coating, no additional requirement in that. Now, by using this, it would give developer, construction company a much faster construction time. You need not to do this protection, preparation, and so on. So it's a much, much cheaper or economical construction method. If this HPI is used, either we or our applicator, they would give a 10 years performance guarantee. Now, the performance guarantee which I want to emphasize is that while it is not a material guarantee, so that paper doesn't tell you that, well, yeah, this product will perform as it's said. We're talking about real performance guarantee. So if you find that, well, you have water comes in, we are liable. Now, if we are using a traditional way to build a basement, it is very, very time consuming. You need to do the binding layer, preparation surface, your membrane, protection, then you can cast the slab. For the wall, you do the same thing. You cast the wall, you prepare the surface, you apply the membrane and protection before you call it job done. So it's very complicated and time consuming. Now, a lot of these speakers already telling you reduce construction time, including L&T, because shorter construction time. Time is very expensive, especially the place I'm in, Singapore. Time is 5 times, actually more. Now, this is one of the very interesting projects which we did. This is in Singapore Metro. They call it Bobby God, is the name of the project. Now here, one of the challenging situation is that while in year 2000, technology is not like today. You have this hyperplastic sizer, self-compacting concrete, no. But the roof of this station is actually under a canal. So in between the roof and the canal, there is no working space. The only way is that you pump the concrete into that gap. You cannot vibrate it. So we and the ready-mix work out a formula that it looks like self-compacting concrete. In fact, it's just high slump concrete. So they pump the concrete into that gap, but cannot compact it. After this formwork take out, they see the roof. They only see a couple of the air pocket that has water drips through. Then we prove to them that, well, how effective this material is. Once they repair the grout, the water droplet, water doesn't move to another place and come out. Now compare to a traditional concrete, where you grout A, it moves to B, you grout B, it moves to C, because the concrete absorbs water. This roof is while using a concrete which doesn't absorb water. So you have a real fast repair. And after that, today, if you walk down to this station, the ticket hall, the roof is there. And until today, so it's about 25 years. It's still performing well. 15 years, sorry. Now this is an interesting job. We done this job in 1983. It's in Hong Kong. You see that the basement is actually in the sea. That the two red building there. Under that two building is a basement. Originally, the consultant, Monso, specified membrane, but the contractor rejected it. He said, I can't do it. So he suggests to use HPI concrete from us. And you look at it, the building. Outside the building is the pier. Now, they are using a high-performance concrete. But that when we were told that after 15 years, they find moisture appear on the surface of that high-performance concrete, whereby our concrete inside the basement is bone-dried. So this is a very significant difference in between this and this high-performance concrete. Now this is the inside of that basement. This was taken about 30 years, the picture. You can see that, wow, it is absolutely dried. Now this is a comparison of high-performance concrete. They use this high-performance concrete with silica film, low water cement ratio, high cement content, plus increased cover. But this is merely about 9 years. And then you find that it corrodes. Now, this is another job done by them, but using our HPI concrete. It was done in 2001, and we take the picture at 2014. It still performed nicely. So, okay, well, I know my time runs up, and I do not want to take up too much of your time. But if you would like to consider this, my representative here called New Tech, you can always contact them. Okay, thank you.
Thank you very much, Mr. Sung.
You're welcome.
It was a very nice presentation.
Thank
Sir,
you.
can I put in my words, like whenever you have some problem, you go to doctor for treatment. And here you are avoiding doctor. There will no problem, no disease, and why do we need doctor? Then how the doctor will earn his livelihood, sir? That's the problem.
I would say it's quite true. We are not only doing these new projects, but we are actually help to fix a lot of those corroded projects. In here, we did some project in Visa, right? Yep. In Philippines, we fixed some of the corroded jetty, and in Malaysia, we did the same thing. And in Indonesia, we do the same thing. It can be done. You need not to really demolish it.
Yeah. So I'm having one query, sir. Yeah. How HPI percentage is decided to mix in the concrete, or what is the percentage is efficient in working with the concrete? And so how we are ensuring all pores or percentage of the pores filled? You are saying pore blocking material. This is HPI is the pore blocking material.
Yeah.
So how much percentage of the pores, how you can assess the percentage of the pores was blocked by this solution or this concrete?
Basically, the rule of thumb is the percentage of pores that you have in the concrete. It varies between 6% to 14%. So based on the concrete that you're doing, the grade of concrete basically, and the density that you have inside. So based on those formulas we've achieved, based on our experience earlier, we've come up with the proportion of 8 liters, 15 liters, and 30 liters, depending upon the absorption that takes place in the concrete.
That
so
is per a meter cube, you are trying to say?
Yeah, for the meter cube, for the meter cube. Okay. So everything is on your absorption, basically. So if you take care of those things, I think we feel that 100% pores would be blocked using the volume that we are suggesting to.
Yeah, is there any surplus material? Is there, means how it will behave?
It doesn't matter because it reacts.
How it will behave? Like let's say
it
bleeding,
doesn't react at
it's
all.
kind of bleeding kind of thing, segregation.
It doesn't react at all because it reacts only with the free lime, available in the concrete.
Okay.
And once the reaction is done, it's permanent for life.
Okay, so my question is, it is actually excess material, so you poured, for example, instead of 10 liters, you mix it as...
If you put even a double, doesn't matter.
Oh, where it will come, how it will collect actually. So
Sir,
that is, it is, so through capillary, it will come to the surface of the concrete, or how it will behave?
Sir, those are polymers, nanoparticles, which are highly compressible.
Okay.
Okay. So it will occupy the space inside and form a plug as we've shown you.
Okay.
So there's no problem.
Okay. Okay. Thank you. Thank you.
Thank you very much, sir. Now, before I invite last presentation, actually, Mr. Rao Garu has come to make an announcement. If we do not finish session before 7, he will cancel the cultural program. So it is up to all of us. So if you want to see the cultural program, you have to finish the fourth presentation before 7, including question, answer, everything. So now, fourth presentation, last presentation of the day, Engineer Seelam Prasad from ACECON, case study on the influence of pre-stress induced elastic shortening on vertical elements of building system. Mr. Seelam Prasad.
Thank you, sir. I think this is a so different topic, so compared to all concrete technologies we are having last day and today and maybe tomorrow also. But as a PT post-tensioning guy, so we want to show some of the things which is even though it is related to strains, concrete strains actually. This is one of the element of the concrete strain by using the post-tensioning in the buildings. So as post-tensioning is also widely using in building sector. So and as per the latest codal changes or codal comments, what are we are having. So what is the impacts? Everyone is having so much panic on what is the influence of post-tensioning on the vertical members. Okay, so we done some case studies actually. We are trying to present here. So now pre-stress is widely used in this modern technology. And so basically why we are using post-tensioning is for longer clear spans, thinner the slab thicknesses, and more flexible and more efficient and reduced cracking, those kind of things. And we are having, what is the immediate effects while doing the post-tensioning is elastic shortening will have. And here what we are trying to do is research concern here is, does this axial shortening will have any influence on the vertical members, right? And shear walls. And possible impact is, yes, there might be a influence on the vertical member forces. So how much it will be there, how to move forward, actually we are trying to present here. And so the object of this one is, so we are inducing the pre-stressing forces and what is the elastic shortening we are going to get to study and to examine with multiple case studies. So varying different structural systems and with different stiffness of the vertical elements. And to understand how the behavior is. These are the primary thing we took here. And so coming to the approach, which kind of approach, how to assess these things actually. So we are having the next thing. And here actually, we applied the pre-stress force as a nodal forces I think everyone is aware of the post-tensioning. We will have the tenons inside the slab. Wherever the tenons is there, so we are going to apply as a nodal forces. Very initial days, substitute frame method STAD or ETAPS initial days, we used to apply the nodal forces similar way. And we are utilizing the ETAPS model for apply this nodal forces, because each and every structural, that means each and every building will have the ETAPS model with the consultant, either ETAPS or STAD. We are utilizing those things. And focus is majorly on the vertical members, behavior of the moments, how it is affecting, and where the impact of pre-stressing will be there. And what are the outcomes from this means elastic shortening effects, and how we are linking to the codal compliances. Next, actually, the basic thing here is the basic behavior of the frame, how it will be there for the gravity load as well as the axial forces, horizontal axial forces, let us say post-tensioning forces. The first frame you can see, that is the regular BMD for the gravity load. The second one is, once we applied the pre-stressing, as the tenons are not concentric, the tenons are eccentric tenons, it will induce some upward forces, that means the load balancing will be done. Due to that, we will have some bending movement, which is majorly in the reversal. And apart from that, we are having the axial shortening will be there. So axial shortening will have some impact on the vertical elements, as it is not simply supported and it is not separated from the vertical elements. Okay. And now we are having some references. Okay. So where the shortening has to be considered, where we have to be ignored, there is some guidelines is there. That is Technical Report 43. This is developed by Post-Tensioning Institution, where the pre-stress, application of the pre-stress, that means axial compression in the floor plate is less than 2 MPa, and the building is less than 50 by 50. So these effects is very nominal, can be ignored. Okay, and having only 1 or 2, central cores or stiff cores. Okay, if the stiff cores was increased because of the building floor height, whatever the reasons, core is increasing, or bulky columns is increasing, and building is more than 50 meters, and because of the loading criteria functionally changes, the pre-compression is exceeding 2 MPa. So we need to take care of this secondary effects or axial shortening effects on the building frames. So far actually in buildings, everyone, we are aware of it. The buildings are designed for partial pre-stressing elements. Okay, any buildings, because bridges actually pre-stressing may be up to fully self-weight, load balancing might be done. Whereas in buildings actually, 60 to 80% of the self-weight only we are doing the load balancing. Those are very partially pre-stressed elements actually. Okay, with that 60 to 80% of partial pre-stressing, we are achieving the requirements of the codal as well as the industry requirements, like lesser the slab thickness, economical, that means costing and all the things. So now one more class is there in 1893, which is stating recently either draft code or recent code, the effects of elastic shortening arising out of the pre-stressing, either pre-tensioning or post-tensioning, if any, of the horizontal members, namely beams and slabs, has to be taken care. Okay. So now the previous slide, we are saying if the pre-compression is very less, it can be ignored. Now our code is saying it has to be studied. Okay. So now to move forward, what are the elements which are causing the elastic shortening? Okay. So one is, if we are having any stiff columns or bulky columns, those are very restrained elements actually. Those will not allow to have the pre-compression. So those are the major issues for us to have more shortening. Those are not flexible. Okay. And coming to the buildings actually, what are the shortenings we are having? One is elastic shortening we are getting from the pre-stressed elements. Apart from that, we are having shrinkage and creep. Already is there inbuilt in the concrete. If you see right side actually, what are the things we are having? The thermal shrinkage, dry shrinkage and creep, if you see the values actually, those are 650 into 10 power 6 minus 6 is there, okay, inbuilt inside the concrete. Whereas elastic shortening is approximately 100 into 10 power minus 6 only. So those is depends, so these values was indicative presented by technical report 43 with respect to 2 MPa. So that means the percentage of the induced elastic shortenings due to the post-tensioning members having with 2 MPa is only 100. That means 1 by 750 means it is only 12% only. Remaining 88% is by the concrete itself. Okay, so we have to understand the issue. So where we are, so why we need to worry actually because of the post-tensioning. Okay, so there are other elements is there, so where it is causing the shortening of the buildings. Okay, and now this shrinkage and creep can be minimized. That means 650 into 10 power minus 6 is there. Those strains can be minimized by adopting some of the construction practices, like we are having the pore separation, we are having the pore strips, shrinkage strips, those kind of things we can implement, and we can reduce the monolithic action with that around 50 days or something, means we can eliminate by around 50% of these creep and shrinkage strains we can eliminate actually. So this is the one thing in generally post-tensioning structures actually, as the building length is more than 50 to 60 meters, we need to have some pore strips. These pore strips will facilitate to reduce these creep and shrinkage strains up to some extent actually. This is inbuilt advantage we are giving in the post-tensioning slabs. It will help us to, we will say pore strips is basically for stressing activity as well as the pore control. Indirectly, it is helping to reduce the creep and shrinkage strains. And how to evaluate this one actually? So we are having two things. One is the basic, fundamental theory, sway theory. Second one is we have to apply the forces by using any softwares actually. Okay. And now, from the sway theory, you can see if we don't have any stiff walls, means actually the elastic shortening will have impact on only the end columns, end base. Whereas stiff members is there, means stiff member will not have any flexibility to move, so it will have from only one side this elastic shortening. So those impacts actually we need to study. So here we can use our fundamental theory, sway theory. So if the fixed condition means, so how much the moment influencing because of the shortening. Let's delta is the shortening from the pre-stress, like that we can assume. And one more is the cantilever. So during the construction stage, the building is while doing the pre-stressing for the particular floor, we may not get fully fixity, full fixity we may not get. It may be a partial fixity, so the moment induced because of the pre-stressing may be in between the fixed and cantilever somewhere we may fall actually. So we can calculate by this way, but those values actually is pure, conservative side will be there. So we can do other methods. So now we are going with applying the pre-stress forces on the any 3D software. We are choosing ETAPS. Before going to that actually, how to evaluate whatever the mechanism we are choosing, applying the nodal forces, it is the values is as in the right way or not actually. We want to assess the methodology what we are choosing actually. So now what we done here is actually, we know axial shortening, that means delta value. So from that we can calculate the temperature drop. That means this is a reduction in the slab, that means temperature dip we can calculate actually. So we are applying and testing actually both application of the nodal forces versus the temperature dip, both is giving the same results or not. So based on that we are applying this technology or this approach to the real-time projects. So now we can see, so we can calculate very easily from the strain, what is the value we are having actually, delta. From that we can calculate the temperature. So this is the approach so we are taking first to move forward. And now this is a single frame we took actually. The pre-compression is greater than 2 MPa. As TR43 was stated that if more than 2 MPa, no need this mechanism. But we chosen P over A is 2.94. And this is the frame, 12 meter grid we taken, 500 deep beam. And based on that we calculated here we know the axial shortening. Okay, based on the temperature is 11 degrees K, minus 11 degrees. So now we applied this one, and we are seeing the shortening forces. Let us say left side one is nodal forces application, right side one is temperature drop. Okay, so axial shortening is 0.588, and then so 0.644. So almost, so majorly single decimal variation only. So we can say it is very nearistic. And you can see because of that, the moment variations is 90 and 98. Okay, so hardly there is a 10% variation is there in both mechanisms for single grid. Now we extended this one to the multiple grids. That means, so we went for the one more floor. Okay, now you can see surprisingly the mechanism both actually, where we applied the PT now, the first level we applied PT, second level also we applied PT. Okay, the behavior is changed actually. The reason is actually the building height is increasing. So the behavior was changed actually. Now you can see the both values more or less same. So axial shortenings also more or less same. So, and the values, bottom values previously single level is there, means PT. This so, sorry. So 98 is there, and we applied so one more level. So 125, 114 is there. And the below level of application of the PT, that means I applied first level, second level, the first level having some variation in the bending moment. So now I am going for a third one actually. Okay, so now you can see the impact is only on the, if I am going move on, floor by floor, means the impact is only the application of the PT, the first level of the application of the PT only, that impact is there because we are having the flexibility as the building height is increasing. The columns is more flexible than so lower level actually. Okay, so the approach is the deformation, that means axial shortenings as well as the BMDs actually, so more or less falling in the same line actually. With this approach actually, so we felt whatever the mechanism we took as a nodal forces, okay, we can continue as both values more or less same actually. Now this is the one more exercise. So what we are trying to say is the impact of the post-tensioning is there only at the first level of application of the pre-stressing, then rest of the levels is it may not having significant impact. And now we extended the same philosophy to the horizontal, so multiple grids actually. So this also same mechanism we are having. The variations is very so nominal actually, right? So with this, we are trying to extend for live jobs with some case studies actually. So now the thing is actually, so lot of the codal revisions we are having from 2016, previous to 2016, now we came once again 2025. So what is the implications of codal things means? Yeah, yes, right. So the thing is, so the code now is recommending to have more and more stiff vertical members, right? So obviously the requirement will change. That means the construction, the building requirement is changed actually. Similarly, if the more and more stiff elements means actually the client also looking for the more spacious things because he is losing his area 2% or 3% so for the vertical members. So the configuration of the buildings is changed actually now. So this is the configuration of building before 2016 or 2015, right? So one core will be there, we'll have multiple grids actually. So now the configuration of the building is becoming like this. We will have one central core, the building is either extended left side, right side, both sides actually, not more than 20 meters. Okay, so this is the client having two grid system actually. That means let us say 16 meter or 20 meter, he is converting into two equal spans of 10 meter, or so 11 and 12 like that. And few more clients actually, they want only core, they want only perimeter beams. Okay, this is one more configuration. Because as the configuration changing, the pre-compression values will change. Because span is increasing means you need to have more pre-compression. Now this is one more configuration. Now this is actually so booming, actually everyone wants this one, clear. So central core, 14 to 15 meter beam with 4 to 5 meter cantilever with perimeter beam. Okay, so now we took actually 3 jobs with this configuration. So in general, as I told earlier, the pre-compression is also in buildings generally 60 to 80% of the self-height we are doing. The pre-compression generally fall around 1 to 1.5 MPa only. So whereas we took 3 cases, first case is 1.2, 1.12 MPa. Second one is with a 3 MPa as a grid beam system. Third one is actually the structural system in the building will change. Some floors will have perimeter beams with one-way slab system. After some floors, actually, two-way beam system will be there. The functional system will change, actually, okay? So those also one case we took, actually, how it will happen. So what is the scenarios like that? As we seen, actually, the application of the pre-stress only affecting at the first level of application. If the functional changes, so structural system change happen at some elevated level, the column, how it is so affecting, actually, we want to see, okay? So we chosen, so as per the industry, what is the regular grid systems happening in the industry, right? So now the first job is this one. We took, this is the central core with so perimeter beams with the small cantilevers. So now we applied, so only now the nodal forces we are applying because we are assessed that the nodal forces is effectively is working. So we were picked this one, we are moving forward with this. And now these are the so general details. Now nodal forces, this is the tunnel layout, and nodal forces was applied, right, for entire floor. And these are the axial force what we applied. So as I told now, pre-compression we are applying 1.12. Generally, our force will be, effective force will be around 110 kilonewton. So 110 into 1.2 you are taking means around 265, 250 will come. Okay? And these are the 1.22 MPa is there. Axial pre-stress, whatever we took, and this one both are in the same line. Okay, so other direction also. Now the same thing, entire building footprint we took, actually, we want to study the columns. So now you can see the same configuration we are having. The application of the pre-stressing here is actually from the first level, actually. So, okay, so here, so we are having the column number A. A represents the envelope without PT. This is the global models, including the lateral load systems, actually. So the B is only the PT effect. That means a shortening effect because of the post-tensioning. The C is a combination of, that means so PT plus envelope plus PT. If you see, the force difference is only, so 181, hardly 265 is the moment from the elastic shortening. Okay, if you go in the blow-up way, the increment in the moment is actually around the first level where the PT is applied now. So that level is having more influence around 50%, and lower level having 16%. Rest of the areas there is no influence is there. Now, even the moment is increasing. You can see 392 to 605. It seems the percentage looking like a high, but the value is actually very less. You can see the AST provided, AST demand actually. AST provided is so versus AST demand is only hardly, so 1.17 versus 1.29. Hardly actually, so 0.1% only is increasing. But this is not the drawing related. The values is based on the software only we took actually. We will have some buffer in the drawings actually. If you say the percentage wise you are saying means 0.1 by 1.2, 1 by 12 hardly. So 8% increment in the steel at that particular level is coming actually. So design, as a designer we will have 5 to 10% excess reinforcement. So we can move forward actually. Okay?
Sir, please conclude, sir.
Yeah, so I'm coming. So 2 minutes only, max 2 minutes. Okay? So this is so other direction. So previously, so one direction of the column we took. Now this is M22 direction, X and Y direction. Here also the percentage is actually different because it depends on the structural system actually. So other direction, the column having around 50% increment in the moment. Here the increment is very less. Okay. Now one more grid I am going. Actually, this is the grid slab system. Here my pre-compression levels is high, around 3 MPa. So in this configuration, this is a rib beam system. Okay. Here you can see the variations is around 20% only, but provided AST is so taking care of those things actually. So now this is one more so column. Here also more or less same actually. This is the third one actually as the pre-compression. That means the structural system is changed actually up to MLCP. MLCP having 7 floors. One structural system is there. Office floors having different structural system. Okay. So here, so orientation of the PT also changing actually. This is actually horizontal beam versus also vertical so system. Others one is actually structural system is changed, vertical beam and horizontal slab. Okay, configuration of the structural system was changed actually. So here you can see, here also locally, so where the application of the PT is at upper ground floor only here, then office 2 is the structural system configuration change actually. Those 2 levels only minorly, so impacted rest of the areas, there is no impact actually. If you see here also, our conclusion is same. This is the walls actually. The columns was modeled as a walls, okay, these are the walls actually. The reinforcement, if you see, there is no change in the reinforcement, so increment, whereas the percentage of the moment is, so looks like a high as it is a wall actually, okay. So based on this actually what I am trying to so conclude is, the level of application of the pre-stress is the, so impacting, where we are applying the, so having minor variations on the vertical elements, right? The level of application of the pre-stress and at the lower level, 2 levels only having the some marginal impact on the vertical members, okay? Rest of the levels is not having much impact. And it depends on the amount of pre-compression and the stiffness of the structural system. And in general, the force increment in the range of 5 to 15% only. But whereas you don't have the significant increment in the reinforcement, okay? And so it depends on level of pre-compression, stiffness of the vertical members, and structural systems adapted. As a conclusion, as a whole, the pre-stress induced effects have a negligible impact on the vertical members. But yes, we are having yet to do something. We need to see more and more structural arrangements, so that means structural systems with the different functionality we need to study further. And for this, we are linking any practical, that means so theoretical versus practical. So in site level, practically, we can able to measure this elastic shortening for 2-3 different grid systems, and we can correlate with this one, means it will give so significant relief to the structural consultants, because everyone is too much panic by seeing the so 1893 so codal implications or codal clause actually. As a PT post-sanctioning agency, so we are there in this field more than 21 years. We are trying to establish the significance of the vertical that means what pre-stressing on the vertical elements is very nominal. It can be well controlled, and whatever the reinforcement, so here and there increment is there also, it will be around less than 5% only, because I presented here the major complicated and so full-scale projects actually, okay. We are not done for anything for this presentation actually, so we are there, the live jobs actually we presented to you. Okay, thank you for this opportunity.
Thank you, Mr. Prasad, for the wonderful presentation and to enlighten us with the impact on the vertical elements because of elastic shortening of pre-stress. In fact, I was looking, it's not like present, it's a workshop. You were taught very well. And I think ICA should go ahead with organizing a workshop on this subject. Thank you very much, and all the 4 presenters done a wonderful job, excellent topics, and we all are entertained also, educated, entertained. Thank you very much. Lot 7, I think some formalities left or completed? The moment you cross 7, you have to cancel the cultural program.
Yeah, thus we have come to the end of the last technical session of today, and without wasting much time, because already it was cautioned by our Venkateswara Garu and Dr. Bansalji that the cultural program will be cancelled if it is beyond 7. So I now request Vinay Gupta ji to felicitate the first the session chair and the speakers. I now call upon the session chair, Dr. Shishil Bansalji. Yes, sir.
In fact, I'm benefited because of 4 speakers.
Yes, sir.
Suggestion by Vinay Gupta, it adds more meaning to it. Yes. Thank you.
The first speaker, Mr. Amit Barde. Amit Barde, sir? Then, he's in the hall, okay. C.A. Prasad, on his behalf, someone is there? Amit Barde, okay. C.A. Prasad ji. Sir.
style of Hyderabad, yes. Thank you.
Engineer Anthony Singh, thank you, sir. Engineer Anthony Singh. Thank you, sir.
Yes, Mr. Anthony. Such a cool, such a comfortable, such a pleasant before the date of presentation. First, the Indian powers in Hyderabadi style. And Mr. Vijay Naidu, why not you also? Yes. Please come.
Yes, sir, please come. आप भी आइए, entire team.
We have an extra flower.
Yes.
Yeah. Yeah.
All the sessions were really wonderful. I'm fortunate to be here. Amit Bade, sir. Amit Bade, sir, has come. Yes. Yes, sir, please. Please, sir.
तुम्ही आला होता तिकडे कळलं तुम्ही इकडे आला होता presentation.
Yes.
Mr. Amit.
Yes. Engineer Salim Prasad. Prasad ji, आप भी.
Mr. Amit Bade.
Amit Bade ka. Amit Bade from L&T.
I will do anything for a photo with you. So I become just
We want to become famous, sir. That's the
Yes.
अभी आए.
Please come.
Yes, you also come. You also please come. Sir.
We were talking about Yukon today in Vishasamudra. Hi sir, how are you sir? Very detailed, very detailed. And you rightly said, Dr. Bansal, that it was more like a workshop. But we've had your workshop in Nagpur recently.
Yes, sir.
Yes. On pre-stressing.
Yes, sir.
And in fact, I will also join for Yes.
Yes.
I will call my team also, sir.
That adds value to us.
Prasad ji, आप भी. Bansal ji, आप भी. It's a great opportunity for us with taking a photograph with all of you. Yes. Yes, sir.
Sir, please invite me.
Yes, please.
Yes, Yukon
Aye,
team.
Yukon. Entire team.
Share the memento. Thank you.
Thank you all for the wonderful session. On behalf of ICA Hyderabad Center as well as organizing committee of ACECON 2025, I thank you one and all.